You might think space has a simple up and down, just like your bedroom ceiling and floor. But when scientists first tried to map what lies above and below our solar system, they discovered something that challenged everything they thought they knew about direction itself. The universe, it turns out, has no real ceiling or basement, no fixed orientation at all. What we call above and below in space are just human inventions, frameworks we created to make sense of an endless expanse that follows no rules we're familiar with. Reality is far stranger than the simple up and down world we experience every day. For centuries, astronomers assumed space worked like Earth, with clear directions and boundaries. They were shocked to learn that our entire solar system sits inside an invisible bubble, that massive streams of particles flow along cosmic highways, and that most of what surrounds us is completely invisible matter we can't even detect. In this video, we'll explore these surprising discoveries about what actually exists above and below us in the cosmic sense, and learn how our tiny perspective fits into something unimaginably vast. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel, and it helps others find it too, just like you did. Thank you. Now, let's get started. In the vastness of space, there really is no up or down. When we think about what sits above our solar system and what sits below it, we're already making assumptions that don't quite work the way they do here on Earth. Space doesn't have floors or ceilings or any kind of universal reference point that tells us which way is which. Scientists had to create their own system, their own way of making sense of direction, when there isn't any natural direction to follow. They took the flat plane, where all our planets orbit around the Sun, and they called that their reference line. Everything on one side of that plane, they call north. Everything on the other side, they call south. It's completely arbitrary, really, but it gives us something to work with. What's fascinating is how this connects to Earth's own spin. The direction we call north in space, that's the same direction as Earth's North Pole, just extended outward into the galaxy. So when we talk about what's above our solar system, we're really talking about what lies in that northward direction from the plane of planetary orbits. The Sun doesn't just sit quietly in space, minding its own business. It's constantly throwing out charged particles in every direction, creating what scientists call the solar wind. This wind creates a massive bubble around our entire solar system, stretching far beyond where any of our planets orbit. This bubble is called the heliosphere, and it's absolutely enormous. The boundary of this bubble sits billions of kilometers away from us. Out there, the solar wind finally meets resistance from the thin gas that drifts between the stars. That boundary shifts and moves, like the edge of a soap bubble floating in air. But it's always there, wrapping around our solar system like invisible protection. This bubble exists above our solar system just as much as it exists below it. It's our first layer, the first thing we encounter when we ask what surrounds us, and it's not just empty space inside this bubble either. The solar wind fills it, carrying the influence of our Sun to incredibly distant places. Beyond that protective bubble lies something called the interstellar medium. It sounds like it should be empty, like the space between stars should contain nothing at all. But it's actually filled with gas and dust, just spread incredibly thin. A cubic centimeter of this space might contain only a few atoms, where the same amount of air you breathe contains trillions upon trillions. Above our solar system lies a particular pocket of this interstellar medium, something astronomers have named the local interstellar cloud. It's not dense enough to see, not dense enough to feel, but it's there. It presses against our heliosphere, shaping that protective bubble around us. In a way, our solar system is swimming through this cloud. Like a boat moving through incredibly thin fog, there's something poetic about realizing that what we call empty space is actually filled with the breath of the galaxy. These wisps of gas and dust, they're the raw materials from which new stars might one day form. They carry traces of elements created in the hearts of dying stars, scattered across vast distances. When scientists look in the direction they call the North Galactic Pole, they're looking above not just our solar system, but above our entire galaxy. Picture our galaxy as a flat disk, filled with spiral arms of stars. From our position inside one of those spiral arms, looking north means looking up and out of that disk entirely. In that direction, we see fewer of our own galaxy's stars, and more of what lies beyond. We get clearer views of other galaxies, distant collections of stars that exist in the vast spaces between galaxies. Looking south takes us in the opposite direction, down and out of our galactic disk, toward another window into the broader universe. These directions matter because they give us our clearest views of cosmic structures that exist on the largest scales. Above and below our galaxy's disk, we can see how galaxies cluster together, how they form vast webs of matter, separated by enormous empty regions. The galactic halo surrounds our entire galaxy, extending far above and far below the disk, where most of the stars live. This halo contains ancient stars, some of the oldest in our galaxy, formed when the universe was much younger. It also contains dark matter, mysterious stuff that we can't see directly, but that makes up most of the mass in our galaxy. Scattered through this halo are globular clusters, tight balls containing hundreds of thousands of ancient stars. These clusters orbit our galaxy at great distances, some of them sitting far above the galactic plane, others far below it. They're like cities of old stars, preserving information about what the universe was like billions of years ago. What's remarkable is how these structures mirror each other. What lies above our solar system has its counterpart below. The heliosphere extends in both directions. The interstellar medium surrounds us from all sides. The galactic halo wraps around our entire galaxy, above and below the disk where we live. This symmetry reminds us that we're not sitting at the bottom or top of anything. We're embedded in the middle of nested structures that extend in all directions. Our solar system sits within our galaxy, which sits within larger groupings of galaxies, which sit within even larger structures that span hundreds of millions of light years. The local group of galaxies, which includes our Milky Way, contains about 50 galaxies in total. Most of them are small, but a few are large spiral or elliptical galaxies like our own. This local group is itself part of an even larger structure called the Virgo supercluster. These cosmic structures exist above and below us in the sense that they extend in all directions from where we sit. There's no preferred orientation, no cosmic up or down that makes more sense than any other. The universe looks roughly the same in every direction we look, at least on the largest scales. But on smaller scales, the view changes dramatically depending on which way we look. Looking along the plane of our galaxy, we see the dense band of stars that creates the Milky Way in our night sky. Looking perpendicular to that plane, above or below it, we see much clearer views of distant space. These different views remind us how our position shapes what we can see. We're not outside observers looking at the universe from some neutral vantage point. We're participants, embedded deep within cosmic structures that determine how the universe appears to us. The matter that surrounds our solar system, both above and below, tells the story of cosmic evolution. The light elements in the interstellar medium were forged in the first few minutes after the Big Bang. The heavier elements were created in the cores of stars and scattered into space when those stars died. This ongoing cycle of stellar birth and death has been enriching the galaxy for billions of years. Each generation of stars creates heavier elements, then scatters them into space where they become raw material for the next generation. We're made from atoms that were once inside stars that died long before our solar system formed. The concept of direction becomes fascinating when you leave Earth's surface behind. Up here, we're used to up and down being obvious. Gravity pulls things toward the ground, and that's that. But once you venture beyond our atmosphere, those reliable markers disappear completely. Scientists had to create their own version of up and down for space. They picked a starting point, the flat disk where our planets orbit around the Sun. This disk isn't perfectly flat, mind you. Each planet's orbit tilts just a little bit, like plates stacked slightly askew on a table. Earth's orbital path became the main reference line, Astronomers call this the ecliptic, and it serves as their cosmic ruler. From this imaginary flat surface, they drew lines extending outward into space. One direction became north, following Earth's spin axis. The other became south, pointing the opposite way. This might sound completely arbitrary, and in some ways, it is. But here's where it gets interesting. Our entire galaxy, the Milky Way, also forms a flat disk shape. Most stars, gas clouds, and cosmic dust concentrate in this thin galactic plane. When we point north or south from our solar system, we're actually pointing away from this crowded stellar neighborhood. Picture it like this. You're standing in the middle of a busy town square. The north and south directions lead you out of the crowd, toward quieter suburbs where you can see farther distances. That's essentially what happens when we look above or below our solar system's plane. The Milky Way stretches across our night sky, like a faint river of light. When you see that band, you're looking along the galaxy's disk, into the thick of billions of stars. But those darker patches above and below that bright band, those lead toward emptier regions of space. Our solar system sits within one of the galaxy's spiral arms, called the Orion Arm. It's actually just a small branch, not even a major arm of the galactic structure. From this position, above us lies what astronomers call the galactic north. Below us stretches the galactic south. Both directions lead away from the stellar crowd into regions with fewer stars, but plenty of their own mysteries. The scale of these directions changes dramatically, depending on how far out you're thinking. Close to home, above and below, might refer to regions just beyond Neptune's orbit. Out there you'll find the Kuiper Belt, populated by icy chunks, dwarf planets, and the occasional comet. Even farther out, theoretically anyway, sits the Oort cloud. This enormous spherical shell of icy objects surrounds our entire solar system. The distance is so vast that the cloud extends nearly halfway to our nearest stellar neighbor. These frozen remnants mark the very edge of the sun's gravitational influence. On this smaller scale, above and below, led to regions where comets wait patiently in the cosmic deep freeze. Something occasionally nudges one of these icy visitors, sending it on a spectacular journey toward the inner solar system. But expand your view much farther, and above and below, reach into the galactic halo. This faint, extended region surrounds the Milky Way's flat disk like a cosmic atmosphere. The halo contains some of the galaxy's most ancient stars, leftover fragments from smaller galaxies that our Milky Way consumed long ago. The halo also holds vast amounts of dark matter, that mysterious invisible material that helps hold galaxies together through its gravitational pull. Above and below, then, lead us into regions rich with this unseen influence. We can't observe dark matter directly, but we know it's there because of how it affects the motion of stars and bends the path of light traveling through space. These directions offer something else valuable to astronomers. Looking above or below the galactic plane means peering through less gas and dust. The view becomes clearer, like looking through a clean window instead of a dirty one. This gives scientists better vantage points for observing distant galaxies and studying the cosmic background radiation, that faint afterglow from the universe's early days. None of this stays still, of course. Our entire solar system races around the galactic center at roughly 828,000 kilometers per hour. One complete orbit takes about 225 million years. During Earth's entire history, we've made the trip around the galaxy only about 20 times. As we orbit, the solar system also wobbles slightly above and below the galactic plane. Picture a bead sliding along a string that gently bounces up and down as it moves in a circle. Over tens of millions of years, we drift upward through the galactic disk, then downward, then back up again. This cosmic bobbing motion affects our local environment in subtle ways. We encounter different regions of interstellar space, experience varying levels of cosmic radiation, and potentially even influence Earth's climate patterns over geological timescales. The wobbling motion reminds us that above and below aren't fixed directions at all. We're constantly moving through them, experiencing different cosmic neighborhoods as millions of years pass by. These directions also lead us toward some of the galaxy's most ancient structures, globular clusters, dense balls containing hundreds of thousands of old stars, orbit in the galactic halo above and below the main disk. These clusters formed when the universe was much younger, and they preserve clues about the early conditions that shaped our galaxy. The emptier regions above and below don't mean empty of everything, though. Besides dark matter and ancient star clusters, these areas contain faint streams of stars, remnants from smaller galaxies that ventured too close to the Milky Way. Our galaxy's gravity gradually stripped away their stars, leaving ghostly trails that astronomers can still detect today. Scale becomes crucial when discussing these cosmic directions. The same words, above and below, can refer to distances that differ by trillions of times. You might be talking about the space just beyond Pluto, or you might mean the vast reaches of intergalactic space where our galaxy's influence finally fades away. This layering of different scales creates a kind of cosmic perspective that's both humbling and exciting. We exist within multiple nested structures, each with its own rhythm and timescale. The solar system orbits within the galaxy. The galaxy moves through its local group of neighbors, and that entire group participates in even larger cosmic flows. Perhaps most remarkably, much of what lies above and below remains hidden from us. Dark matter fills these regions, but we can only detect its presence indirectly. Faint structures might exist beyond our current ability to observe them. The directions we've mapped so carefully still hold countless secrets, waiting for more sensitive instruments and deeper understanding to reveal them. The human mind has this remarkable ability to take the most familiar concepts and stretch them across impossible distances. Think about directions like up and down. These ideas make perfect sense when you're standing in your living room or walking down the street. But somehow we've managed to apply these same simple concepts to the entire galaxy itself. It's almost like taking a ruler, meant for measuring a table, and deciding to measure the distance between cities with it. Yet this mental stretching isn't just possible, it actually works. When we look at our position in the galaxy, there's something both humbling and empowering about the experience. The sheer scale can make you feel incredibly small, like a grain of sand on an endless beach. But then you realize that this very feeling, this ability to comprehend our smallness, is actually a demonstration of something quite extraordinary about human consciousness. We can hold these vast concepts in our minds, organize them, and use them to navigate through ideas that would otherwise be completely overwhelming. The framework we create when we talk about galactic directions serves as more than just a convenient way to describe things. It transforms chaos into something we can actually discuss and explore. Without these reference points, the cosmos would feel like trying to give directions in a city with no street signs or landmarks. Everything would be relative to everything else, in ways that make no practical sense. But with our framework of above and below, we suddenly have a way to talk calmly about regions of space that stretch across distances our ancestors could never have imagined. Light plays a fascinating role in defining these cosmic directions. When astronomers point their instruments away from the galactic plane, both above and below our solar system, they encounter something quite remarkable. There's this faint glow that permeates everything, a kind of cosmic background noise made of light itself. This radiation represents the leftover warmth from the Big Bang, still traveling through space after billions of years. It's everywhere in the universe, spread out evenly, like the last traces of heat from a fire that went out long ago. The interesting thing about observing this ancient light is how our galactic neighborhood affects what we can see. The disk of our galaxy, packed dense with stars and clouds of gas and dust, acts like a thick fog that obscures our view. It's similar to how city lights can wash out the stars at night, except on a galactic scale. But when we look above or below the galactic plane, the view clears up dramatically. Suddenly, this primordial radiation shines through much more cleanly, giving us one of our best windows into the earliest moments of the universe. This creates an almost poetic situation, where the directions we call above and below aren't just arbitrary choices for navigation. They actually represent our clearest pathways to understanding the deepest history of everything that exists. It's as if the universe arranged itself in such a way that by simply looking up or down from our galactic perspective, we gain access to its most ancient secrets. Movement adds another layer of complexity to this cosmic stage. High-energy particles, born in some of the most violent events the galaxy has to offer, stream toward us constantly from every direction imaginable. These cosmic rays carry tremendous energy, far more than anything we can create in our most powerful particle accelerators. They're like messengers from distant catastrophes, stellar explosions, and other cosmic violence that shaped the galaxy long before our solar system even existed. Our sun creates a protective bubble around us called the heliosphere, which deflects some of these incoming particles. But it's not a perfect shield. Many cosmic rays still make it through, especially when approaching from above and below our solar system. Scientists study the patterns of how these particles arrive, where they seem to come from, and what energy levels they carry. It's like cosmic archaeology, piecing together the story of distant events by examining the debris that eventually reaches our neighborhood. The directions above and below become part of this detective work. By tracking which cosmic rays come from which directions, researchers can trace their journeys backward through space and time. Each particle carries information about its origin, the environments it passed through, and the magnetic fields that deflected its path along the way. It's remarkable to think that by studying the direction something approaches Earth, we can learn about explosive events that happened thousands of light years away and millions of years ago. All of these elements, the ancient light, the cosmic rays, the protective boundaries, the galactic structure, they combine to create something far more complex than a simple bubble floating in empty space. Our solar system sits embedded in a rich, dynamic environment with multiple layers, shifting boundaries, constant motion, and deep historical connections to the rest of the galaxy. It's like being in a house that's part of a neighborhood, which is part of a city, which is part of a region, except each level involves physics and scales that challenge our everyday understanding. The concept of above and below gives us a way to organize all this complexity into something we can actually think about and discuss. Without this framework, the interconnections would be overwhelming, like trying to understand a symphony by listening to every instrument at once, without any sense of structure or arrangement. But with our directional reference points, we can examine one layer at a time, one region after another, building up a comprehensive picture of where we actually are in the grand scheme of things. This process of building understanding through familiar concepts reveals something fundamental about how human consciousness works. We start with what we know, the immediate and tangible, then gradually extend our understanding outward into realms that would otherwise be completely abstract. It's a kind of intellectual bridge building, where each new concept connects to something we already understand, creating pathways for exploring ideas that initially seem impossible to grasp. Every second, our sun throws massive streams of charged particles into space. These particles, racing away at hundreds of kilometers per second, create something remarkable, a protective bubble that wraps around our entire solar system. This bubble exists because the sun isn't quiet. It's constantly in motion, constantly active. The outer layers of the sun's atmosphere get so incredibly hot that particles there gain enough energy to break free from the sun's gravity completely. Once they escape, the sun's magnetic field sweeps them outward, carrying them deep into space. What we're talking about here is plasma, a mixture of protons and electrons that have been stripped from the sun's corona. The corona is the sun's outermost atmosphere, and it reaches temperatures that are almost impossible to imagine. Hot enough that matter itself changes its behavior. These particles don't just drift away slowly, they stream outward in all directions, creating what we call the solar wind. And this wind doesn't stop, doesn't slow down until it hits something strong enough to push back against it. For billions and billions of kilometers, there's almost nothing out there to stop these particles. Space between the stars is mostly empty, with only the thinnest possible gas scattered throughout. This is why our sun's influence can reach so incredibly far, the boundary where our sun's particles finally meet resistance. That's where our solar bubble forms. Scientists call this bubble the heliosphere, and it represents something profound about our place in the universe. We don't live in raw interstellar space. We live inside a sheltered region, protected by our star's constant activity. Think about what this means for a moment. The very star that gives us light and warmth also wraps us in an invisible shield. The same nuclear processes that make life possible on Earth also create this vast protective envelope around our entire cosmic neighborhood. The heliosphere has layers, though they're nothing like the layers of an onion you could peel away. They're more like gradual changes in the flow of cosmic wind. Close to us, the solar wind streams freely outward, but as it travels farther and farther from the sun, it eventually starts to encounter the thin gas of interstellar space. When the solar wind first meets this resistance, it creates what's called the termination shock. This is where the wind suddenly slows down, becomes turbulent, gets compressed and heated. It's like a river hitting a dam, except this dam is made of incredibly thin interstellar material. Beyond the termination shock, the solar wind continues outward, but now it's different. It's no longer the free-flowing stream it was closer to the sun. It's been changed by its collision with interstellar space. Even farther out lies the true edge of our solar bubble. This boundary is called the heliopause, and it represents the place where the pressure of our sun's wind exactly balances the pressure of the interstellar medium. Here, the influence of our star finally gives way to the influence of the galaxy itself. The heliosphere extends in all directions, above the solar system, below it, to every side, but it's not perfectly round like a soap bubble. The solar system is moving through the galaxy at tremendous speed, and this motion shapes our protective bubble. Scientists think the heliosphere looks more like a comet than a sphere. The protective bubble, scientists think the heliosphere looks more like a comet than a sphere. It has a rounded front face that pushes against the interstellar medium as we move through it. Behind us, it stretches into a long tail, thinned out because the solar wind can expand more easily in the space we've already passed through. This shape matters more than you might think. It affects how cosmic rays and other high-energy particles from deep space can enter our neighborhood. Depending on which direction they come from, these particles might be blocked completely, or redirected around us, or allowed to slip through. The scale of this bubble is almost impossible to grasp. The distance from the Sun to Earth is about 150 million kilometers. That seems enormous until you consider that the distance from the Sun to the edge of our solar bubble is around 18 billion kilometers. Light, the fastest thing in the universe, takes about 8 minutes to travel from the Sun to Earth. That same light takes more than 16 hours to cross from the Sun to the edge of the heliosphere. 16 hours, traveling at the speed of light, just to cross the bubble created by our star's breath. This immense structure defines what we mean by the solar system in a very real way. Not the orbits of planets, though those are important too, but the actual reach of our Sun's influence, the extent of its protective embrace. 2 spacecraft have actually crossed this boundary and entered interstellar space. They've sent back data showing us what it's like outside our cosmic bubble. The measurements confirm what scientists suspected, that we truly do live inside a protected region, sheltered from the harsher environment between the stars. The thickness of this protection varies depending on solar activity. When our sun is more active, throwing out more particles, the bubble grows stronger and pushes farther into space. When solar activity is lower, the bubble becomes weaker and interstellar space can press closer to us. There's something almost poetic about this arrangement. Our sun, burning through nuclear fusion in its core, creates not just the light that warms our planet, but also this vast invisible shield that surrounds our entire cosmic neighborhood. The same processes that make photosynthesis possible also deflect harmful cosmic radiation away from us. 2 remarkable machines, launched back in 1977, have become humanity's most distant messengers. The Voyager spacecraft have been traveling outward for decades now, carrying our curiosity into the deepest reaches of space. These mechanical explorers crossed a boundary that most people don't even know exists, a border that marks where our sun's influence finally ends. In 2012, Voyager 1 made history by crossing something called the heliopause. 6 years later, Voyager 2 followed. Their instrument detected the moment when everything changed, when the familiar solar wind that had pushed them outward for so long suddenly faded away. The transition happened slowly, gradually, but it was unmistakable. Beyond this invisible line, they entered the true space between stars. These spacecraft are still out there right now, sending back signals that travel for hours before reaching Earth. Each faint whisper carries information about a realm no human has ever experienced directly. They're our first taste of what lies beyond the protective bubble that surrounds our entire solar system. This bubble, this heliosphere, isn't just some abstract concept that only interests scientists. It actually keeps us alive in ways most people never consider. Out there in the galaxy, violent events create streams of high-energy particles, cosmic rays that race through space at incredible speeds. Supernovas blast these particles outward, along with other cosmic catastrophes we can barely imagine. These particles carry enough energy to tear apart DNA, to fry electronic circuits, to slowly strip away the atmospheres of planets. Earth faces this cosmic bombardment every single day. But most of these dangerous particles never reach us, because the sun's wind creates a shield around our entire solar system. The heliosphere deflects countless cosmic rays that would otherwise make life on Earth much more difficult. Our planet has its own magnetic field, of course, which provides a second layer of protection, but the heliosphere is the first line of defense, the outer wall of our cosmic fortress. It's not perfect. Some radiation still gets through, but without it, Earth would be a much more hostile place. The sun creates this protective bubble through a constant stream of charged particles flowing outward in all directions. This solar wind races past all the planets, past Pluto, past the distant objects of the Kuiper Belt. It keeps flowing until it finally meets the interstellar medium, the thin gas and dust that fills the space between stars. Where these two forces meet, that's where the boundary forms. When we think about the solar system, we usually picture planets orbiting the sun, maybe some asteroids and comets. But there's another way to define our cosmic neighborhood. Everything inside the heliosphere belongs to the sun's domain. Everything beyond it belongs to the galaxy. In this sense, the Voyager spacecraft were the first human creations to truly leave home. Scientists are still trying to understand the exact shape of this bubble. For years, they thought it looked like a comet, with a long tail streaming behind as our solar system moves through the galaxy. Recent evidence suggests it might be shorter, more rounded, sculpted by complex magnetic fields that twist and bend in ways we're still figuring out. The boundary itself isn't a smooth, perfect sphere. Cosmic rays leak through some areas more easily than others. The solar wind slows down and changes direction as it encounters different densities of interstellar gas. These variations create a complex, turbulent edge zone, where the sun's influence gradually fades away. This entire structure breathes like a living thing. The sun follows an 11-year cycle, sometimes more active, sometimes quieter. During active periods, the solar wind grows stronger, pushing the heliosphere outward. During quiet periods, the wind weakens and the bubble shrinks. The edge of our solar system can shift by billions of kilometers, expanding and contracting with the rhythm of our star. There's something profound about realizing that the boundaries of home are always moving. The edge of everything familiar to us shifts constantly, responding to forces we can't see or feel. Right now, as you listen to this, that distant boundary is somewhere different than it was yesterday. Our sun isn't unique in creating such a bubble. Every star with a stellar wind carves out its own protective zone in space. These cosmic bubbles can overlap, press against each other, or leave gaps in between. The galaxy is filled with these structures, each one a star's attempt to claim a piece of space as its own. The space above us and below us, beyond our heliosphere, contains this vast network of stellar influences. Some bubbles are larger than ours, created by more massive stars with more powerful winds. Others are smaller, weaker, offering less protection to anything that might orbit within them. They form a patchwork across the galaxy, constantly shifting, as stars are born, age, and die. Understanding these bubbles helps us grasp our place in the cosmic hierarchy. We exist within nested layers of protection and influence. Earth's magnetic field protects us from the solar wind. The heliosphere protects us from galactic cosmic rays, and perhaps the galaxy itself provides some protection from the even more extreme environment of intergalactic space. The Voyager spacecraft continued their journey outward, still functioning after more than 4 decades in space. They're now sampling the true interstellar medium, measuring its density, temperature, and magnetic properties. Every piece of data they send back helps us understand not just our own cosmic neighborhood, but the fundamental nature of the space between stars. These mechanical ambassadors carry golden records, messages intended for any alien civilization that might someday find them. But perhaps their greatest message is simpler: the fact that curious creatures from a small planet had the audacity to send emissaries beyond the protective bubble of their birth star. They represent our first tentative steps into the true cosmic ocean that surrounds us. When we observe our local stellar environment carefully, it reveals fundamental patterns about how all stars interact with their cosmic neighborhoods. Each star in the galaxy creates its own sphere of influence, pushing against the surrounding interstellar medium with streams of charged particles. Our Sun's version of this phenomenon teaches us about stellar physics on a universal scale. Future space exploration depends heavily on understanding these boundaries. Any probe venturing beyond our solar system will encounter a dramatic shift in conditions once it crosses this invisible barrier. Inside our star's domain, radiation levels follow predictable patterns. Magnetic fields behave in familiar ways. Outside, the rules change completely. Mission planners face a challenge when designing interstellar spacecraft. The environment beyond our stellar bubble remains largely mysterious. 2 Voyager probes have crossed this threshold, sending back data from opposite directions that space is 3-dimensional, vast and varied. What lies above and below the plane of our solar system might tell entirely different stories. The connection between our star and our planet extends far beyond simple warmth and light. Solar storms launch waves of energetic particles outward, riding the stellar wind like surfers on cosmic waves. Some reach Earth within days, lighting up our skies with auroras, disrupting satellites and power grids. Others continue their journey for years, eventually reaching the outer boundaries where our Sun's influence meets galactic space. These disturbances travel upward and downward from the solar system's disk, carrying the Sun's signature into regions where planets never formed. Even at the most distant edges of our stellar domain, solar activity leaves its mark. The breath of our star reaches farther than most people imagine. Picture our Sun as constantly exhaling, creating an enormous bubble in space. This stellar wind pushes outward in all directions, carrying magnetic fields and charged particles. Where this flow meets the thin gas drifting between stars, pressure builds up, creating a boundary. Inside this region, our star dominates. Outside, galactic forces take control. The transition happens gradually, then suddenly. Like a soap bubble meeting still air, there comes a point where the outward push can go no further. The interstellar medium pushes back with its own pressure, creating a balance. This invisible wall surrounds our entire solar system, extending high above and far below the plane where planets orbit. Standing under a clear night sky, nothing suggests such a barrier exists. Stars appear scattered across open space, distant but accessible. The darkness between them seems empty, inviting. Yet we live perpetually inside this protective cocoon, shielded by our star's constant output of particles and energy. This realization transforms how we might think about our place in the cosmos. We often consider ourselves residents of a planet, orbiting a star within a galaxy. But we're also inhabitants of a stellar bubble, breathing recycled star stuff, protected by magnetic fields that stretch billions of miles in every direction. The boundary above us mirrors the one below us. Space has no up or down in any absolute sense. But relative to our solar system's disk, the bubble extends equally in all directions. Whatever lies beyond in the galactic north also awaits in the galactic south, regions where our sun's voice grows quiet and the galaxy's larger conversation begins. The sun creates something that scientists call the heliosphere, a name that comes from helios for sun and sphere for the space it fills. This invisible cocoon wraps around our entire solar system, stretching far beyond any planet we can see. When you think about Neptune, sitting roughly 4.5 billion kilometers from the sun, you might imagine that's pretty far out. But the heliosphere, this protective bubble, extends more than 18 billion kilometers away. That's several times farther than our most distant planet, creating a massive shield that contains our whole solar system, with plenty of room left over. Inside this enormous bubble, solar wind rushes outward at incredible speeds, carrying the sun's magnetic field along for the ride. As the sun spins, it twists this magnetic field into a spiral pattern, much like a rotating lawn sprinkler, creates curved streams of water. This spiraling magnetic field, called the heliospheric magnetic field, fills the space above us, below us, all around us. The spiral shape isn't just pretty to think about. It actually controls how charged particles move through space, how cosmic rays get deflected, and how energy flows in our cosmic neighborhood. Without this twisted magnetic structure, our little corner of the galaxy would be a very different place. One of the most important jobs this heliosphere does is protecting us from galactic cosmic rays. These are particles that have been accelerated to nearly the speed of light by distant supernovas and other violent cosmic events. If these particles hit our solar system directly, they would bombard Earth and the other planets with dangerous radiation. The heliosphere acts like a cosmic umbrella, deflecting many of these high-energy particles, slowing others down, scattering them at the boundary. It doesn't block them completely. Nothing could do that, but it reduces their intensity dramatically. Without this protection, life on Earth would face much higher radiation levels, and all the technology we depend on would be constantly damaged. For decades, scientists debated what shape this protective cocoon actually takes. The early thinking was that it looked like a comet, with a rounded nose pointing in the direction our solar system travels through the galaxy, and a long tail streaming behind us. Picture a cosmic teardrop, stretched by our movement through space. But more recent data from spacecraft and computer simulations suggest something different. The heliosphere might actually be more like a rounded bubble, without that long trailing tail. The exact shape gets determined by complex magnetic interactions, forces we're still trying to fully understand. What's fascinating is that whatever the final shape turns out to be, it's definitely not uniform or static. The heliosphere gets squeezed in some directions, stretched in others, constantly reshaped by competing forces. From the outside, interstellar matter pushes against it, while from the inside, the rhythm of the solar wind pushes back. This creates a dynamic boundary, always shifting, always responding to the cosmic environment around us. In a way, it's like we're living inside a soap bubble that's being gently squeezed and stretched by invisible hands, never quite settling into a perfect sphere. The heliosphere represents something profound about our place in the universe. We tend to think of space as empty, hostile, but here we have this enormous protective structure, billions of kilometers across, created by our own star. It's a reminder that even in the vastness of space, there are boundaries, there are neighborhoods, there are zones of influence and protection. The cosmic bubble we call home stretches in all directions around us, reaching far beyond the planets we know. This invisible shield, formed by our sun's constant stream of particles, doesn't expand uniformly in every direction. Instead, it bulges and contracts based on the pressures it encounters from the space between stars. Think of it as a living, breathing boundary, rather than a solid wall. The forces that shape this cosmic cocoon are always shifting, always finding new balance points between our star's influence and the mysterious medium that fills the galaxy. Two robotic explorers gave us our first real glimpse of this boundary's nature. As they journeyed outward through our solar system, these mechanical ambassadors encountered a dramatic shift in their environment. They passed through a region where the sun's wind suddenly slowed down, like a river hitting a dam. Beyond this point, they entered a chaotic zone filled with turbulent particles and twisted magnetic fields. Eventually, they crossed into true interstellar space, where the sun's influence finally fades away. The data they transmitted back to Earth revealed something remarkable. The number of particles from our sun dropped dramatically, while particles from deep space increased. These measurements proved that our protective bubble really exists, that it has complex internal structure, and that crossing its boundary creates detectable changes in the cosmic environment. For the first time in human history, we had physically touched the edge of our star's domain. This cosmic breathing has more immediate effects than you might expect. When our sun becomes more active, blasting stronger winds into space, our protective bubble inflates like a balloon. During calmer periods, it shrinks back down. This rhythmic expansion and contraction directly affects how many high-energy particles from deep space can penetrate into our solar system. During active solar periods, when our bubble is largest and most robust, fewer cosmic rays make it through to reach Earth. When the sun quiets down, more of these energetic visitors slip past our defenses. Scientists have connected these variations to long-term changes in our planet's climate and weather patterns over thousands of years. It's a humbling reminder that our world doesn't exist in isolation. We're constantly influenced by the cosmic cocoon we inhabit, breathing in rhythm with our star's activity cycles. Understanding this protective shell becomes crucial as we dream of venturing deeper into space. Human explorers traveling beyond Earth's own magnetic shield will face a radiation environment shaped entirely by our sun's cosmic bubble. Even robotic spacecraft already deal with these challenges, but for living astronauts, the stakes become much higher. Knowing exactly how our cocoon provides protection, where its weak spots might be, and how it changes over time becomes essential knowledge for planning journeys to Mars and beyond. People above us, below us, in every direction. This invisible barrier stands between us and the harsh environment of interstellar space. The boundary itself is far from peaceful. Where our sun's influence meets the interstellar medium, violent processes unfold continuously. Magnetic fields twist and snap back together, accelerating particles to incredible speeds. The edge of our cosmic home buzzes with activity we're still trying to fully comprehend. These turbulent processes teach us about more than just our own neighborhood. Every star in our galaxy creates its own version of this protective bubble. By studying how these stellar cocoons work, we gain insights into how stars might shield their planets, potentially making life possible on distant worlds. Our sun's bubble is just one example in a vast population of these cosmic shields scattered throughout the galaxy. Young, energetic stars blast out powerful winds that create enormous, forceful boundaries. Older stars, having burned through more of their fuel, produce gentler winds and smaller protective zones. Our middle-aged sun, at roughly 4.5 billion years old, creates a cocoon that reflects its current life stage. The balance between our star's outward push and the inward pressure from interstellar space determines the exact size and shape of our cosmic home. This balance won't last forever. As our sun continues aging over the next several billion years, its activity will change, and so will our protective boundary. Eventually, when our star swells into a red giant, the cocoon will transform dramatically. Later still, as the sun sheds much of its mass, our cosmic shield will fade away entirely. The protective bubble we've always known is temporary, tied to the life cycle of the star that created it. In cosmic terms, even our most permanent seeming features are just temporary arrangements, waiting for time and stellar evolution to reshape them into something entirely new. Every star in our galaxy breathes out a protective bubble around itself, and our sun is no exception. These stellar cocoons, called astrospheres, create invisible shields that wrap around entire solar systems. When we look at distant stars through our telescopes, we can actually detect these bubbles by studying how starlight changes as it passes through their boundaries. The light carries tiny signatures, like fingerprints, that tell us about the properties of these faraway protective shells. Our own stellar cocoon, the heliosphere, becomes a reference point for understanding this cosmic phenomenon. It's fascinating to think that what surrounds us here is happening billions of times over throughout the Milky Way. Each star system sits nestled within its own invisible shelter, shaped by the constant stream of particles flowing from its central star. Protection in space works like nested Russian dolls, with shields inside shields. Earth sits at the center with its own magnetic field, deflecting harmful particles that would otherwise strip away our atmosphere. This magnetic bubble extends thousands of miles into space, creating our first line of defense. Beyond that, the heliosphere forms a much larger protective zone, stretching far past the orbit of Pluto. And beyond even that, the galaxy itself has magnetic fields that guide and influence how cosmic particles move through interstellar space. Think of it as 3 layers of cosmic armor. Earth's magnetosphere is like a personal force field. The heliosphere is our neighborhood security system, and the galactic magnetic field is the overarching structure that governs particle movement on truly vast scales. Each layer serves its purpose, filtering out different types of radiation and harmful particles. The heliosphere extends roughly 100 times farther from the Sun than Earth's orbit. That's an almost incomprehensible distance, yet it's all part of our solar system's protective envelope. Without this middle shield, cosmic rays would bombard our planet with much greater intensity. These high-energy particles from deep space could damage our DNA, disrupt our technology, and make life far more challenging than it already is. What makes this cosmic protection so remarkable is how invisible it remains to us. We can't see the heliosphere's boundaries with our eyes. We can't step outside and admire its shape or watch it deflect incoming threats. Everything we know about it comes from careful measurements, from studying how particles behave when they encounter it, and from the faint signals sent back by spacecraft that have ventured to its edges. The Voyager probes, launched decades ago, have traveled farther from home than any human-made objects. They've crossed the boundary where our sun's influence fades and interstellar space begins. Their instruments have measured the subtle changes in particle density, magnetic field strength, and radiation levels that mark this cosmic transition. Through their data, we've learned that our heliosphere isn't a perfect sphere at all, but rather an elongated bubble shaped by our solar system's movement through the galaxy. This invisible shield has been quietly doing its job for billions of years. It's the reason Earth's climate has remained stable enough for life to emerge and evolve. Without the heliosphere's protection, our planet would face a much harsher cosmic environment. The early atmosphere might have been stripped away entirely. Complex chemistry would struggle to develop under constant bombardment from high-energy particles. Every breath you take, every moment of life on this planet, exists within this vast protective cocoon. The heliosphere doesn't just surround our solar system, it defines the very environment that made our existence possible. It's a reminder that even in the apparent emptiness of space, there are structures and boundaries that shape everything within them. Our sun's constant outflow of particles, the solar wind, creates this bubble not through any conscious design, but simply as a consequence of being an active star. The solar wind travels at hundreds of miles per second, carrying the sun's magnetic field with it. When this fast-moving stream meets the slower, denser material of interstellar space, it creates a boundary, a place where our star's influence gives way to the broader galactic environment. The size and shape of our heliosphere changes over time as our solar system moves through different regions of the galaxy. Sometimes we pass through areas where interstellar space is denser, compressing our protective bubble. Other times, we encounter regions that are more sparse, allowing the heliosphere to expand. These cosmic seasons play out over millions of years, far longer than human timescales, yet they influence the environment around Earth in subtle ways. Understanding astrospheres around other stars helps us appreciate how common this phenomenon might be. Nearly every star likely creates its own version of a heliosphere. Some might be larger than ours, some smaller, depending on the star's size, age, and activity level. Young, energetic stars probably blow enormous bubbles, while older, quieter stars might have more modest protective zones. This cosmic architecture exists on scales that challenge our intuition. When we think of the solar system, we usually picture the planets orbiting the sun. But the true boundary of our solar system, marked by the heliosphere's edge, extends far beyond the last planet. It's a three-dimensional structure, invisible yet real, that encompasses everything we call home. The particles that make up the solar wind started their journey in the sun's core, where nuclear fusion creates the energy that powers our star. These particles work their way to the surface over thousands of years, then race outward to form the very wind that shapes our protective bubble. In a sense, every atom in the solar wind carries a piece of the sun's energy to the farthest reaches of our cosmic neighborhood. There's something profound about living within this stellar breath, this constant exhalation from our sun that creates a haven for life. The heliosphere connects us to our star in ways we rarely consider, extending the sun's influence far beyond its visible light and warmth. It makes our entire solar system feel less like isolated objects floating in empty space, and more like a unified system, bound together by invisible currents and magnetic fields. Beyond the protective boundary of our solar bubble lies something that challenges our intuition about emptiness. The space between stars, this vast interstellar medium, stretches across distances so enormous that light itself, racing at its ultimate speed limit, needs years to cross from one side to another. Yet this apparent void holds secrets that reshape how we think about cosmic architecture. The interstellar medium contains just a handful of atoms scattered through each cubic centimeter of space. Compare this to the air surrounding you right now, packed with trillions upon trillions of molecules in that same tiny volume. The difference feels almost absurd. But here's where cosmic perspective shifts everything, where small numbers become mighty across the canvas of space. Those few lonely atoms spread across light years accumulate into something significant. They bend the paths of starlight, influence how celestial bodies move, and provide the fundamental ingredients for stellar birth and death. It's like finding that individual grains of sand, scattered across a continent, somehow manage to build mountains. Within this sparse medium, density varies in fascinating ways. Think of it as cosmic weather, where some regions remain thin and diffuse, while others gather into what astronomers call interstellar clouds. These aren't clouds as we know them on Earth, fluffy and temporary, but rather concentrations of gas and dust that can stretch across hundreds of light years. Our solar system happens to be traveling through one of these clouds right now. The local interstellar cloud, a relatively warm and gentle region about 30 light-years wide, became our cosmic neighborhood sometime in the recent past, perhaps 50,000 years ago. We'll eventually drift out of it, continuing our long journey around the galaxy's center. But for now, this cloud shapes the very boundary of our solar influence. The heliosphere, that protective bubble created by our sun's solar wind, gets squeezed and molded by the pressure and density of whatever interstellar material surrounds it. It's a dynamic interaction, like a soap bubble floating through air currents, constantly adjusting its shape to the conditions outside. Temperature, in these interstellar regions, spans an incredible range. Some clouds register thousands of degrees, their atoms moving with fierce energy, despite the vast emptiness between them. Others hover just above absolute zero, so cold that atoms barely vibrate, creating conditions where molecules can actually form and survive. These cold, dense regions become stellar nurseries, places where gravity finally wins its patient battle against the dispersed matter. Slowly, over millions of years, material clumps together, grows denser, heats up, and eventually ignites nuclear fusion. New stars are born from this process, along with the planetary systems that might orbit them. When we look up at the night sky, dark patches in the Milky Way often mark these dense molecular clouds. The dust within them is so thick, it blocks the light from background stars, creating what appear to be holes in the star field. Sometimes these same regions glow softly, illuminated by nearby starlight that manages to penetrate and scatter through the cosmic particles. Interstellar dust consists of tiny grains, often smaller than the wavelength of visible light. These microscopic particles form from silicates, carbon compounds, and various ices. They might seem negligible, scattered so thinly through space, but they profoundly affect how we see the universe. Starlight passing through dusty regions becomes dimmed and reddened, like sunlight filtering through Earth's atmosphere at sunset. This reddening effect means that distant stars often appear different from their true colors and brightness. Astronomers must account for this interstellar extinction when measuring cosmic distances or studying stellar properties. It's as if the universe wears tinted glasses, subtly altering our perception of everything beyond our immediate neighborhood. The structure of the interstellar medium reflects the violent history of our galaxy. Stellar explosions, powerful winds from massive stars, and the gravitational dance of celestial objects have carved cavities, compressed regions, and created the complex tapestry we observe today. Each supernova blast creates a bubble of hot, thin gas that can persist for millions of years. These supernova remnants often trigger new star formation in their surrounding areas. The shock waves compress nearby gas clouds, potentially pushing them past the threshold where gravity takes over. In this way, stellar death directly leads to stellar birth, a cosmic recycling program that has operated for billions of years. Heavy elements, those atoms more complex than hydrogen and helium, get distributed through the interstellar medium primarily by these stellar explosions. Every carbon atom in your body, every oxygen molecule you breathe, was once forged in the nuclear furnace of a star and then scattered into space by such violent events. The interstellar medium serves as both the repository and the delivery system for this enriched material. As our solar system continues its orbital journey around the galaxy, we'll encounter different regions of the interstellar medium. Some might be denser, potentially compressing our heliosphere and allowing more cosmic radiation to reach the inner planets. Others might be more diffuse, letting our solar bubble expand further outward. Gas and dust float between the stars, creating what scientists call interstellar extinction. This invisible veil makes certain patches of our night sky appear darker than others. When you look up at the Milky Way, those shadowy lanes cutting through the bright stellar ribbon, that's dust at work, absorbing and scattering light across unimaginable distances. Yet this cosmic dust serves a far grander purpose than merely dimming starlight. Each microscopic grain acts as a gathering point, a nucleus where molecules slowly accumulate over millions of years. These tiny specks become the foundation for everything solid we know. Planets, moons, asteroids, even the ground beneath our feet, all trace their origins back to these wandering particles, drifting in the void. There's something profound about realizing that the space around us contains the raw materials for future worlds. Somewhere out there, dust grains are already beginning the slow process of becoming tomorrow's Earth-like planets. The universe continuously recycles its building blocks, transforming stellar remnants into new possibilities for existence. Magnetic fields weave through this interstellar space like invisible highways. Though incredibly weak compared to the magnets on your refrigerator, these fields stretch across light years, gently steering charged particles along predetermined paths. They sculpt gas clouds into elegant structures, influence where stars will be born, and create an unseen framework that organizes the cosmos. Astronomers can actually map these magnetic fields by studying polarized light from distant stars. The light reveals how these invisible lines of force curve around gas clouds, how they twist and bend through space, above and below our solar system. It's like discovering the hidden architecture of the universe, the blueprint that shapes everything we see. Supernova shockwaves travel through this medium like ripples across a cosmic pond. When massive stars explode, they launch devastating blast waves that compress surrounding gas, heat it to millions of degrees, and set entire regions of space into motion. These shockwaves often trigger the birth of new stars by squeezing nearby gas clamps until they collapse under their own gravity. More importantly, supernovas inject heavy elements into the interstellar medium. The carbon in your body, the oxygen you breathe, the iron in your blood, all were forged inside dying stars and scattered by these explosive events. Without this cosmic recycling program, planets like Earth couldn't exist. Life itself depends on this violent stellar death and rebirth cycle. Our solar system drifts through what astronomers call the local interstellar cloud. This relatively dense patch of gas may itself be the product of ancient supernova explosions. We appear to be traveling through a vast cavity called the local bubble, a region where multiple stellar explosions over the past 10 to 20 million years have swept away most of the surrounding material. If this theory is correct, then the very space we inhabit tells a story of cosmic catastrophe and renewal. The emptiness around us isn't truly empty, but rather the aftermath of stellar violence, shaped by explosions that occurred when our planet was still young. Those ancient shock waves continue to influence the structure of space around us. This interstellar material affects how we observe the universe. Radio waves, X-rays, and ultraviolet light all interact with gas and dust in different ways. When astronomers study distant galaxies or try to detect the cosmic background radiation left over from the Big Bang, they must account for this interference. The interstellar medium acts like a fog, subtly altering the light that reaches our telescopes. Fortunately, the density of this material varies significantly across different directions in space. Above and below our solar system, astronomers have identified clearer windows where less gas and dust block our view. These transparent regions serve as cosmic keyholes, allowing us to peer deeper into space and further back in time than would otherwise be possible. For spacecraft venturing beyond our solar system's protective bubble, this interstellar environment becomes a harsh reality to navigate. What seems like empty space actually contains a constant rain of atoms, dust grains, and high-energy radiation. Engineers must design instruments capable of surviving impacts with dust particles traveling at tens of kilometers per second. The electronic systems on these distant probes must also withstand relentless bombardment by cosmic rays, high-energy particles that can damage computer circuits over time. The Voyager spacecraft, now traveling through interstellar space, send back data confirming these conditions exist, just as scientists predicted. There's something humbling about recognizing that even the spaces between stars pulse with activity and meaning. What appears as emptiness from our earthbound perspective actually teems with the ingredients for future worlds, the magnetic scaffolding that shapes cosmic structure, and the enriched remnants of stellar explosions that made our existence possible. The space between stars holds more secrets than most people realize. Every cubic centimeter out there contains atoms floating quietly in what we call the interstellar medium. This isn't the complete vacuum that many imagine. Instead, it's a thin soup of hydrogen, helium, and cosmic dust particles. Our solar system moves through this material like a ship cutting through ocean currents. The sun drags all its planets along on a journey that takes hundreds of millions of years to complete just one lap around the galaxy. During this epic voyage, we encounter different neighborhoods of space, each with its own personality. Some regions are dense with matter, others are surprisingly empty. Temperature varies wildly too. Hot zones can reach thousands of degrees, while cold pockets hover just above absolute zero. These differences matter more than you might think. They push against our solar system's protective bubble, the heliosphere, changing its shape like wind reshaping a soap bubble. This cosmic weather affects how many high-energy particles, cosmic rays, reach Earth. Over millions of years, these shifts might even influence our planet's climate. The thin matter between stars becomes part of Earth's extended environment, quietly shaping the conditions that allowed life to emerge and evolve. Magnetic fields weave through this interstellar fabric, invisible highways that guide charged particles across vast distances. Shock waves from exploding stars ripple outward, compressing gas and dust into denser clumps. These compressed regions become stellar nurseries, where gravity eventually pulls material together to birth new stars. The galaxy recycles itself this way, constantly. Old stars die and scatter their contents into space. This enriched material drifts for eons before gravity gathers it again into fresh stellar systems. We're made from atoms that once lived inside ancient stars, atoms that spent countless millennia floating through interstellar space before finding their way to Earth. The vastness of this medium stretches imagination. If you could somehow collect all the matter between stars in our galaxy, it would equal about 10 billion times the mass of our Sun. Yet, spread across such enormous volumes, this material remains incredibly thin, far less dense than any vacuum we can create in laboratories. Dust grains drift through this cosmic ocean, each one a tiny world with its own story. Some form around dying stars, others crystallize in the cold depths of space. These particles block and scatter starlight, creating the dark lanes we see cutting across the Milky Way on clear nights. The interstellar medium isn't static either. It churns and flows, driven by stellar winds and supernova explosions. Giant bubbles of hot gas expand outward from clusters of massive stars. Where these bubbles meet cooler material, they create boundaries and structures, giving the galaxy its complex, ever-changing architecture. Perhaps most remarkably, this seemingly empty space serves as a cosmic laboratory. Chemical reactions happen slowly in the frigid temperatures, creating molecules that couldn't exist on Earth. Some of these compounds are organic, the building blocks of life forming naturally in the darkness between stars. When we look up at the night sky, we're seeing through this medium, this active participant in our cosmic story. It's not just empty backdrop, but rather the canvas on which stellar evolution paints its masterpiece. Every photon of starlight we observe has traveled through this material, carrying information about both the star that created it and the space it crossed to reach us. The boundary where our solar system meets this interstellar ocean remains active and dynamic. Solar wind pushes outward while interstellar pressure pushes back, creating a constantly shifting frontier. Space probes have recently crossed this boundary for the first time, sending back data about what lies beyond our cosmic neighborhood. This intersection reminds us that our solar system isn't isolated. We're part of something larger, moving through a galaxy filled with invisible currents and hidden complexity. The space that separates us from other stars also connects us to them, a medium through which matter, energy, and even life's ingredients flow freely across the cosmos. Ideas spin through space like cosmic dancers, each one carrying secrets about our place in this vast universe. The Milky Way stretches around us, not just as that faint ribbon we glimpse on clear nights, but as our actual cosmic address. This enormous wheel of stars, gas, and dust rotates slowly through time, held together by gravity's invisible grip, while dark matter weaves through everything like an unseen thread. Our Sun finds itself tucked into what astronomers call the Orion Arm, a relatively modest spiral structure compared to the galaxy's grander highways. Think of it as living on a quiet side street rather than a major boulevard. This Orion spur, as some prefer to call it, sits comfortably between two much larger spiral arms, Perseus and Sagittarius, giving us a front row seat to observe the cosmic neighborhood without too much traffic. When we crane our necks upward, away from the crowded galactic plane, we're peering into regions that tell stories spanning billions of years. The first thing our telescopes encounter in this direction is something called the galactic halo. Picture a roughly spherical bubble surrounding the entire galactic disk, filled with some of the oldest residents in our cosmic neighborhood. These ancient stars cluster together in what we call globular clusters, dense collections that can contain hundreds of thousands, sometimes millions of stars, all bound together by gravity's patient assistance. They orbit our galaxy like celestial beehives, not confined to the flat disk where most stars live, but scattered above and below it in three-dimensional freedom. Some of these clusters shine faintly in our skies, cosmic fossils from an era when the universe was much younger. The ages of these globular clusters boggle the mind. 10 to 13 billion years old, meaning they formed when the galaxy itself was still finding its shape. In a universe that's roughly 13.8 billion years old, these star clusters are practically senior citizens, having witnessed almost the entire history of cosmic evolution. Between the thin disk where we live and this ancient halo, there's another layer that astronomers call the thick disk. While our local neighborhood in the thin disk bustles with younger stars and fresh gas clouds, the thick disk contains older, more spread out stellar populations. These stars extend much farther above and below the galactic plane, like a cosmic middle management layer. Scientists think this thick disk represents a remnant from the galaxy's more turbulent youth, possibly formed when smaller galaxies crashed into our own, or during periods of intense stellar formation that stirred up the cosmic pot. It's a population that carries the story of how the Milky Way assembled itself, piece by piece, collision by collision, over cosmic time. Our galaxy hasn't lived a peaceful existence, despite the serene appearance of stars in our night sky. Throughout its long history, the Milky Way has been something of a cosmic cannibal, absorbing smaller galaxies that wandered too close. Gravity tears these smaller systems apart, mixing their stars into our galaxy's existing structure, like ingredients in a slow-motion cosmic soup. Some of these ancient mergers left behind visible evidence in the form of stellar streams, long arcs of stars that stretch across the sky like faint cosmic contrails. These streams cross above the galactic plane, ghostly reminders of past encounters between galaxies. Each stream tells astronomers something about how our galaxy grew, how often these cosmic collisions occurred, and how those dramatic events shaped the stellar populations we observe today. Dark matter adds another layer of mystery to this neighborhood above us. Though completely invisible to our telescopes, this enigmatic substance supposedly makes up most of the galaxy's total mass. It forms a vast halo that extends far beyond the visible stars, reaching above and below the galactic disk like an enormous invisible scaffold. The philosophical implications of this cosmic architecture invite reflection on scale and perspective. We exist on a small planet, orbiting an ordinary star, located in a minor spiral arm of a galaxy that has spent billions of years consuming its neighbors and rearranging itself through gravitational dance. The very atoms in our bodies were forged in stellar furnaces, scattered by ancient supernovas, and eventually incorporated into the solar nebula that became our solar system. Every time we look up at the night sky, we're actually looking through layers of cosmic history. The globular clusters above us formed when the universe was a fraction of its current age. The thick disk stars witnessed the galaxy's adolescent growing pains. The stellar streams record cosmic collisions that happened before our sun even existed. This vast structure continues to evolve. Even now, stars are born in nebular nurseries, live their nuclear lives, and eventually return their processed elements to space. Dark matter continues its invisible influence, shepherding the motions of visible matter through gravitational fields we can measure but not directly observe. The Orion Arm, where we reside, provides a relatively stable platform from which to study all this cosmic drama. We're neither too close to the galactic center, where radiation and gravitational forces become extreme, nor too far out in the galactic suburbs where heavy elements become scarce. Our location offers what astronomers sometimes call the galactic habitable zone, a region where conditions favor the complex chemistry necessary for life. The forces that bind our galaxy together work in ways that stretch far beyond what we might imagine. Gravity acts like an invisible thread, weaving through space, holding countless stars in their dance around the galactic center. Without this cosmic glue, everything would simply drift apart, scattered into the void like leaves in an endless wind. There's something almost poetic about how dark matter surrounds us completely. It exists above our solar system, below it, threading through every corner of space we occupy. We can't see it, can't touch it, can't detect it directly, yet it shapes the very motion of stars and entire clusters. This invisible presence guides the choreography of the cosmos, a silent partner in the grand ballet of space. The view changes dramatically when we shift our gaze away from the crowded band of the Milky Way. Looking up above the galactic plane, the sky opens up like a window suddenly cleaned of dust. Down here in the disk, gas and cosmic debris block so much of what lies beyond. But these clearer windows above and below our position become precious gifts for understanding the universe. Through these cosmic windows, we can glimpse the faint afterglow of creation itself. The cosmic microwave background radiation still whispers across the universe, carrying echoes from the Big Bang. Without these clear sightlines, this ancient light would remain hidden behind the clutter of our own galactic neighborhood. These same windows let us survey distant galaxies, placing our own Milky Way into the broader context of the universe. It's like stepping back to see how our own house fits into the neighborhood, the city, the world beyond. Star clusters populate the space above us in fascinating variety. Open clusters gather young stars together, siblings born from the same cloud of gas and dust. These stellar families stay loosely connected, but time eventually pulls them apart. Many live in the thin disk with us, but others venture into higher orbits, carrying youth into the quieter regions above. Globular clusters tell a completely different story. These ancient spheres contain some of the oldest stars in the galaxy, metal-poor relics from an earlier age. They're like fossils embedded in space, marking the galaxy's earliest days with their faint, steady glow. Up in the halo, they drift in quiet orbits, witnesses to billions of years of cosmic evolution. The space above isn't just filled with old, quiet structures, though. Hot gas fountains rise from the galactic disk, pushed upward by the violent deaths of massive stars. Supernova explosions and stellar winds drive this material up and out of the plane, where it cools and eventually falls back down. This galactic fountain creates an active cycle, breathing life through the galaxy structure. High-velocity clouds add another layer of mystery to this neighborhood. These concentrations of gas move at speeds that don't match the disk's rotation, drifting like cosmic wanderers. Some might be the remains of small galaxies being slowly absorbed, their material stripped away and added to our own. Others could be fresh gas falling in from the vast spaces between galaxies, future fuel for star formation. The galaxy itself isn't the neat, flat disk we might imagine. The Milky Way warps and bends, rising on one side and dipping on the other. This cosmic ripple probably comes from gravitational tugs, from satellite galaxies or interactions with the dark matter halo. Looking above the solar system, we're seeing part of this warped architecture, evidence that galaxies are living, changing structures. Our galactic neighbors include small companion galaxies scattered through the space above and around us. Dwarf galaxies like Draco and Ursa Minor orbit the Milky Way, like tiny moons around a planet. Though small and faint, these companions play important roles in the galactic ecosystem. They show us how galaxies interact, how they feed each other material, how stars get traded back and forth across cosmic distances. All these elements, the thick disk with its older stars, the ancient halo clusters, the streaming remains of past mergers, the rising and falling gas fountains, the invisible dark matter scaffolding, create layers of history written across space. Each component tells part of a larger story about how galaxies form, evolve, and change over cosmic time. The neighborhood above our solar system represents more than just scattered matter in space. It's a community with structure, with relationships, with processes that connect everything together. We exist within this vast galactic ecosystem, part of something much larger than our immediate surroundings, yet intimately connected to it all through the same forces that govern everything from the smallest particles to the largest structures in the universe. Somewhere out there in the darkness above us, invisible rivers are flowing. These aren't made of water or anything you could see with your eyes. Instead, they carry some of the most powerful travelers in the entire universe. Every single second, tiny bullets of energy are hitting your body. They pass right through you, completely harmless at this level, but they're there nonetheless. These are cosmic rays, and they've been racing across the galaxy for who knows how long before finally reaching Earth. The name is actually pretty misleading. Cosmic rays aren't rays at all. They're particles, mostly protons and other atomic pieces, traveling at speeds that are almost impossible to imagine, nearly as fast as light itself. These particles were born in some of the most violent places the universe has to offer. Picture a massive star, maybe 20 times heavier than our Sun, reaching the end of its life. When it explodes in a supernova, the blast creates shock waves so powerful they can grab nearby particles and fling them across space at incredible speeds. Some cosmic rays might come from even stranger places. Near black holes, magnetic fields can twist and writhe with such intensity that they act like cosmic particle accelerators. Neutron stars, those impossibly dense remnants of dead suns, can do the same thing. Once these particles get moving, they don't really want to stop. They race through the galaxy, bouncing off magnetic fields, changing direction constantly, but rarely slowing down. It's like they're following invisible highways that crisscross through space. The galaxy is absolutely filled with magnetic field lines. They twist and loop in patterns, shaped by rotation, by turbulence, by all the matter flowing around out there. For charged particles like cosmic rays, these magnetic fields act like guardrails on a winding mountain road. Instead of traveling in straight lines from their birthplace to Earth, cosmic rays follow these magnetic highways. They spiral along field lines, get deflected, change course, sometimes spending millions of years just wandering around the galaxy before they finally arrive here. This makes it really hard to figure out exactly where any particular cosmic ray came from. By the time it reaches us, it might have taken such a twisted path that tracing it back to its source becomes nearly impossible. But in a way, that's part of what makes them so fascinating. Each cosmic ray carries a kind of message about the galaxy's most energetic events. Scientists can study their composition and learn about the processes that created them. Some carry signatures of elements that were forged in the heart of exploding stars. When cosmic rays hit our atmosphere, they don't just disappear. They crash into air molecules and create showers of secondary particles. It's like cosmic fireworks happening constantly above our heads. Completely invisible to us, the higher up you go, the more intense this cosmic ray bombardment becomes. Astronauts have to worry about radiation exposure. Satellites get bombarded constantly. Even airline pilots who fly at high altitudes receive more cosmic ray exposure than people on the ground. Fortunately, we have some protection. The sun creates its own kind of particle flow, called the solar wind. This stream of charged particles from our star creates a bubble around the solar system called the heliosphere. It acts like a partial shield, deflecting some cosmic rays away from us. But the solar wind itself is just one example of something that's happening all throughout the galaxy. Nearly every star produces some kind of stellar wind. Young, hot stars often have really strong ones, shedding mass at incredible rates. These stellar winds don't just disappear into empty space. They interact with all the gas and dust floating between the stars. They carve out bubbles, create shock waves, and mix material around in complex ways. When you combine the stellar winds from billions of stars, you get something like a circulation system for the entire Milky Way. Matter and energy get moved across enormous distances through this network of invisible flows. Sometimes, when many stellar winds combine with supernova explosions, they create what astronomers call superbubbles. These are vast cavities in space, hundreds of light years across, filled with hot, thin gas. The boundaries are marked by shells of compressed gas, where all this stellar activity has pushed the surrounding material outward. Our own solar system happens to be sitting inside one of these structures right now. It's called the local bubble, and it was probably created by multiple supernova explosions over the past several million years. The edges of this bubble extend in all directions around us, marking the boundaries where ancient shock waves carved out this space. What's really remarkable is how all these different phenomena connect with each other. Cosmic rays interact with stellar winds. Both of them follow the galaxy's magnetic field lines. The magnetic fields themselves are shaped by the rotation of the galaxy and by all the turbulence created by flowing matter. It creates this incredibly complex three-dimensional web of invisible highways stretching throughout the Milky Way. Particles stream along magnetic field lines, get deflected by stellar winds, accelerated by shock waves, and scattered in all directions. Above us, below us, and in every direction we could point. This hidden network extends across space. It's always shifting, always changing, but always there. The galaxy isn't just a collection of stars sitting peacefully in the dark. It's a dynamic, active place where invisible rivers of energy flow, constantly. In some ways, it makes you wonder about the nature of movement itself. We're used to thinking about motion in terms of things we can see: cars on highways, rivers flowing to the ocean, birds flying through the air. But some of the most important movement in the universe happens completely beyond our senses. These cosmic highways carry information about the galaxy's past. They transport energy from violent stellar deaths to quiet regions of space. They connect distant parts of the Milky Way in ways we're only beginning to understand. Every cosmic ray that hits your body traveled an unimaginably long path to get here. It might have been accelerated by a supernova that exploded when the galaxy was much younger. It could have spiraled along magnetic field lines for millions of years, following a route so complex that no map could ever capture it. And yet here it is, this tiny messenger from the depths of space, completing a journey that started in one of the most extreme environments the universe can create. There's something almost poetic about that connection between the vast and the intimate, between cosmic violence and the quiet moment of a particle passing through your hand. Deep within the invisible architecture of our galaxy, energy flows in forms that would make our most powerful machines seem like toys. These cosmic rays carry energies that dwarf anything we've managed to create in our laboratories. Picture this: a single atomic nucleus, smaller than anything you could ever see, racing through space at nearly the speed of light. This tiny speck carries the same kinetic energy as a baseball flying through the air after a solid hit, all that power, concentrated into something unimaginably small. When one of these cosmic bullets finally meets Earth's atmosphere, something remarkable happens. It doesn't just stop, it explodes into a cascade of secondary particles that spread out like an invisible firework. This shower of particles can cover areas spanning many kilometers. Finding and studying these rare, high-energy visitors has become one of the greatest puzzles in modern astrophysics. They're messengers from the most violent, extreme processes our universe has to offer. Whatever created them had enough power to hurl matter clear across entire galaxies. But here's where things get philosophically interesting. These same cosmic highways that tell us about the universe's most spectacular events also raise serious questions about life itself. High levels of cosmic radiation aren't exactly friendly to living things. They damage DNA, they strip away atmospheres, they make worlds hostile to life as we know it. Planets that lack strong magnetic fields or thick atmospheric blankets find themselves especially exposed to this cosmic bombardment. This makes us wonder about our own fortunate position. Our heliosphere, that protective bubble created by our sun's influence, might be absolutely essential for life to exist here. We're wrapped in this cosmic cocoon that shields us from the worst of the galaxy's radiation highways. Above us and below us, these streams of high-energy particles never stop flowing, but we remain safely tucked away inside our protective layers. It's a humbling thought that our planet's habitability over billions of years might depend partly on where we sit in the galaxy, and how well we're shielded from these invisible forces. But cosmic rays aren't just destructive wanderers. They play a surprisingly creative role in the galaxy's ongoing story. When these high-energy particles slam into atoms floating in interstellar space, they trigger nuclear processes called spallation reactions. Through these cosmic collisions, new elements get born. Elements like lithium, beryllium, and boron, which stellar fusion rarely produces, owe their existence partly to these particle highways. So the same dangerous radiation that threatens life also contributes to the galaxy's chemical diversity. Above us, invisible streams of particles are literally helping to build the periodic table, creating the very inventory of elements that future stars and planets will inherit. Stellar winds add another fascinating layer to this cosmic recycling program. Stars don't just shine, they breathe. They constantly blow matter away from themselves, returning gas to the space between stars. Over vast stretches of time, this recycled material mixes and cools, eventually gathering itself into new generations of stars and planets. The winds from massive stars carry special significance because they're loaded with heavy elements forged in stellar cores. These stellar exhalations seed the galaxy with the raw ingredients needed for rocky worlds and complex chemistry. The combination of cosmic ray scattering and stellar wind circulation creates one of the galaxy's most important renewal mechanisms. When we step back and picture our galaxy this way, it transforms from a static collection of distant lights into something much more dynamic. It becomes a living system, filled with constant movement and exchange. Streams of particles cross light years in what feels like cosmic heartbeats. Winds push outward from countless stars, eventually colliding and merging with other stellar exhalations. Shock waves carve out enormous cavities in space. Magnetic fields weave invisible paths through all this apparent chaos. The galaxy pulses with motion that our eyes can't detect, but which never stops. From Earth's surface, we often imagine space as calm and unchanging. Those steady points of light in the night sky seem so peaceful, so permanent. But the reality above us tells a completely different story. Space buzzes with invisible highways of energy and matter. Every single second, cosmic rays reach us from distant corners of the galaxy. Every second, our solar wind carries particles away from our star and out into the cosmic medium. Every second, stellar winds from other suns add their contributions to this vast, ongoing mixture. The apparent stillness of the night sky becomes an illusion created by the sheer distances involved. Beneath that calm exterior lies ceaseless motion, constant exchange of energy and matter, highways of the cosmos weaving all around us. This perspective completely changes how we understand our place in the universe. We're not simply sitting in some quiet, forgotten corner of space. We're embedded within a system in constant circulation, connected to distant stars by the particles they continuously send out. We're linked to ancient stellar explosions by the cosmic rays they produced eons ago. We're part of the larger cycle of matter through the winds that carry elements across the galaxy. Above and below, we exist within this cosmic flow, sheltered safely inside our heliosphere, but still immersed in the galaxy's vast traffic patterns of matter and energy. Our galaxy exists as a vast disk, spinning slowly through the darkness of space. Stars, gas, and cosmic dust gather into this wide, flat structure, creating the magnificent spiral we call the Milky Way. But here's something fascinating. There's a special direction that leads us completely away from all that crowded stellar traffic. Imagine stepping through an invisible doorway, leaving the busy neighborhood of our galactic disk behind. This direction exists, and astronomers call it the North Galactic Pole. It's like finding a quiet path that leads straight up and out of the cosmic hustle. The galaxy has its own version of north and south. Just like Earth does, while our planet's poles come from its rotation, the galaxy's poles emerge from the flat plane of its disk. The North Galactic Pole sits directly perpendicular to this plane, pointing straight up into what we might call galactic space. If you could somehow float far above the Milky Way, looking down at its sprawling arms, the North Galactic Pole would be the point directly over your head. From our earthbound perspective, though, this special direction appears in the constellation Coma Berenices. It's a faint patch of sky, easy to overlook, but it carries profound cosmic significance. Looking toward the galactic pole feels completely different from gazing at the Milky Way's bright band. That familiar streak across our night sky bursts with stars, glows with gas clouds, and gets carved up by dark lanes of dust. It's spectacular, but incredibly crowded. Like trying to see through a busy city, the North Galactic Pole offers something entirely different. A region of relative cosmic calm. Fewer stars block our view because we're looking out of the disk rather than along its crowded plane. The dust that normally obscures distant objects becomes much less of a problem. What emerges is a cleaner window, a clearer view into the universe beyond our galactic home. This direction opens outward, like lifting a theater curtain to reveal an enormous stage behind it. The view stretches into deep space, where distant galaxies wait to be discovered. Astronomers love this region precisely because it offers less interference from our own galaxy's busy stellar traffic. When telescopes point toward the North Galactic Pole, they can gather light from galaxies millions, even billions of light years away. These distant systems, normally hidden behind the fog of our own stars, become visible and clear. Scientists use this cosmic window to map the large-scale structure of the entire universe. The cosmic microwave background, that faint afterglow from the Big Bang itself, becomes easier to study in this direction. This ancient radiation fills all of space, that toward the galactic plane, it gets mixed up with emissions from nearby stars and dust. Toward the galactic pole, though, the signal comes through much cleaner. This makes the North Galactic Pole one of cosmology's most important vantage points. Through this window, scientists can glimpse not just other galaxies, but the very earliest light in the cosmos. It's like having a telescope pointed directly at the dawn of time. The region around the North Galactic Pole isn't completely empty space, though. It contains its own collection of galaxies, including members of something called the Coma Cluster. This massive group holds thousands of galaxies, all bound together by gravity's invisible threads. The Coma Cluster sits more than 300 million light-years away from us, yet its presence becomes detectable when we look in this special direction. It represents one of the great structures in our local universe, a cosmic city of galaxies, floating in the darkness. Beyond that cluster, even more galaxies stretch outward, forming part of the cosmic web that makes up the universe's large-scale architecture. When we think about what lies above our solar system, it's natural to focus on nearby things, the sun's influence, local stars, interstellar space. But the North Galactic Pole reminds us that above also means outward. A line of sight that carries us far beyond the Milky Way's boundaries. It's not just about our galaxy's structure, but about connecting our tiny neighborhood to the broader cosmos. Looking in this direction also reveals the difference between the galaxy's disk and its halo. The halo forms a roughly spherical region of older stars and globular clusters, surrounding the disk like a vast, dim sphere. When we gaze toward the North Galactic Pole, we're seeing through this halo. We might encounter faint star clusters, ancient suns orbiting high above the disk, but beyond them, space opens up considerably. This gives astronomers a chance to study the halo itself, understanding its composition and its role in galactic structure. The North Galactic Pole helps us understand perspective in space. On Earth, directions make intuitive sense because we live on a sphere under gravity's pull. North, south, east, west, up, down, these all feel natural and obvious. In the galaxy, though, orientation becomes much less intuitive. By defining a galactic north, astronomers create a cosmic compass, a way to map the sky and know exactly where we're pointing our instruments. When we say we're looking above in galactic terms, we mean this specific direction, aligned with the North Galactic Pole. Our solar system doesn't stay perfectly still within the galactic disk. As the sun orbits the galaxy's center, it oscillates up and down, rising above the plane, then dipping below it over tens of millions of years. This bobbing motion means our relationship to the galactic pole slowly changes. Sometimes we're closer to that cosmic north, sometimes farther away. Over vast timescales, our vantage point shifts, subtly changing the angle of our view. The North Pole stays in the same direction, but our perspective on it evolves, adding another layer of motion to our place in the galaxy. Studies of the North Galactic Pole have revealed crucial information about dark matter. By observing how stars and clusters move in this direction, astronomers can detect the presence of invisible mass. The galaxy's halo of dark matter extends well above and below the disk. Looking toward the pole gives us one of the best views into how this mysterious substance shapes our galaxy. Though we cannot see dark matter directly, its gravitational influence becomes evident in stellar motions. In the quiet direction of the pole, this influence shows up especially clearly. Thinking about the North Galactic Pole can change how we see the night sky entirely. The stars that catch our attention most easily lie along the Milky Way's bright band, numerous and striking. But when we shift our gaze away from that band into darker, quieter regions, we're looking toward the pole. Those fewer stars might make the view seem less impressive at first glance. In reality, though, it represents one of the most profound directions we can look. Beyond those scattered stars lies an open window into the universe's deepest reaches. The North Galactic Pole represents both a direction and a philosophy. It's not a place we could ever travel to, but rather a line of sight that takes us straight out of our disk, through the halo, and into the universe beyond. It reminds us that above isn't just about local structure, but about perspective itself. It's about how we orient ourselves in the vast darkness of space, how we connect our small corner of the galaxy to the larger cosmic story. In that quiet direction, past the scattered stars of our galactic neighborhood, lies a pathway to understanding our place in the infinite expanse of existence. Space holds mysteries that challenge everything we think we know about reality. When astronomers point their telescopes toward distant galaxies, they notice something peculiar about the way these cosmic islands spin. The outer edges of galaxies rotate far too quickly, much faster than physics should allow. Think of it like a spinning record player. If you put marbles on a turntable, the ones near the center stay put, while the outer ones fly off. Galaxies should behave the same way, with their outer stars drifting into space. But they don't. Something invisible must be holding them together. This invisible something, scientists have discovered, outweighs everything we can see by enormous margins. In our own Milky Way galaxy, this unseen material makes up about 80% of all the mass. The stars, planets, gas clouds, and cosmic dust that light up our night sky represent just a tiny fraction of what's actually out there. We call this mystery substance dark matter, though it's not really dark in the traditional sense. It's completely transparent. Light passes right through it, as if it weren't there at all. No telescope, no matter how powerful, can capture its image directly. Yet, its gravitational fingerprints are everywhere. Imagine living inside a snow globe, but most of the snow is invisible. You can see a few flakes drifting around, but you feel the weight of countless others you cannot perceive. That's our situation in the cosmos. We're embedded in a vast halo of this invisible material that extends far beyond the visible boundaries of our galaxy. This halo isn't uniform like a smooth bubble. Computer simulations suggest it's lumpy and streaked, with dense clumps and flowing rivers of dark matter streaming through space. Some of these streams might be leftovers from smaller galaxies that our Milky Way consumed billions of years ago, their dark matter still circulating like cream stirred into coffee. The search for dark matter has become one of science's greatest detective stories. Deep underground, in abandoned mines and beneath mountains, sensitive detectors wait in silence for the faintest whisper of a dark matter particle colliding with ordinary atoms. So far, these underground vigils have yielded only frustrating silence. Particle accelerators smash atoms together at incredible energies, hoping to create dark matter particles in the debris. Space telescopes scan for unusual gamma rays that might signal dark matter interactions. Every approach has revealed tantalizing hints, but definitive proof remains elusive. What makes this mystery even more profound is that dark matter seems to be the scaffolding upon which the entire visible universe hangs. In the early cosmos, before the first stars ignited, dark matter was already clumping together under its own gravity. These invisible clumps attracted ordinary gas, which eventually cooled and condensed into the first generation of stars and galaxies. Without dark matter, the universe might have remained a cold, empty expanse with no galaxies, no stars, no planets, and certainly no life. Every atom in your body exists because dark matter provided the gravitational foundation that allowed complex structures to form. Gravitational lensing gives us another window into this hidden realm. When light from distant galaxies passes near massive concentrations of dark matter, space itself warps like a funhouse mirror. The light bends and distorts, creating multiple images or stretched arcs of the same distant galaxy. By carefully measuring these distortions, astronomers can map the invisible architecture that surrounds us. These cosmic mirages reveal that dark matter halos aren't unique to our galaxy. Every galaxy sits embedded within its own invisible cocoon. Galaxy clusters, containing thousands of individual galaxies, are held together primarily by dark matter's gravitational embrace. The visible galaxies are like fireflies scattered throughout vast, invisible clouds. Our local neighborhood of galaxies, including the nearby Andromeda galaxy, forms a gravitationally bound group. The dark matter halos of these galaxies may actually overlap, creating an invisible web that spans millions of light years. We're not just inside our own galaxy's dark matter halo, we're also swimming through the extended halos of our cosmic neighbors. Some theorists propose that dark matter consists of weakly interacting massive particles, exotic cousins of the protons and electrons that make up ordinary matter. Others suggest it might be composed of ultralight particles called axions, so ghostly they barely interact with anything at all. More radical theories question whether dark matter exists as particles at all, proposing instead that our understanding of gravity itself needs revision. The philosophical implications stretch beyond physics into the realm of human perception and knowledge. We pride ourselves on being observers of the universe, yet we're apparently blind to most of what exists around us. It's humbling to realize that our senses, and even our most sophisticated instruments, reveal only a small slice of reality. If we could somehow develop dark matter vision, the night sky would transform dramatically. Instead of seeing isolated points of starlight against black emptiness, we might perceive vast glowing structures. Streams of dark matter would arc across the heavens like aurora, marking the paths of ancient galactic collisions. The familiar constellations would appear embedded within enormous, faintly luminous clouds. This invisible universe extends far beyond our local galactic neighborhood. Galaxy clusters, the largest gravitationally bound structures in the cosmos, contain more dark matter than ordinary matter by factors of 5 or 6 to 1. These clusters are connected by filaments of dark matter that span hundreds of millions of light years, forming what cosmologists call the cosmic web. Between these filaments lie vast voids, regions where both ordinary and dark matter are scarce. Yet even in these seemingly empty spaces, dark matter provides the subtle gravitational influences that guide the evolution of cosmic structure. Nothing in the universe escapes its influence. The search continues in laboratories around the world. New detector technologies promise greater sensitivity to the faint signals that dark matter particles might produce. Next-generation telescopes will map the cosmic web in unprecedented detail. Theoretical physicists develop increasingly sophisticated models to explain how invisible matter could hide in plain sight. Perhaps the most profound aspect of the dark matter mystery is how it reframes our relationship with the cosmos. We are not separate observers looking out at the universe from a distance. We are participants, embedded within and moving through this invisible medium that permeates all of space. Every breath you take, every step you walk, carries you through a sea of particles that remain completely mysterious to science. The universe has revealed itself to be far stranger and more complex than early astronomers imagined. What appears to be empty space teems with invisible activity. What seems solid and permanent floats within vast unseen structures. The cosmos is teaching us that reality extends far beyond the reach of human senses, challenging us to expand our understanding of existence itself. Picture stepping away from a bustling city center, where neon lights flash and crowds gather, and walking into the quiet suburbs, where older houses sit peacefully under streetlights. This is what happens when we shift our gaze from the bright spiral arms of our galaxy to the galactic halo that surrounds everything we know. The halo wraps around our entire galaxy like an enormous, invisible bubble. It stretches hundreds of thousands of light years in every direction, making our familiar Milky Way disk look tiny by comparison. While the disk measures about 100,000 light years across, it's only a few thousand light years thick, like a dinner plate floating inside a basketball. Scattered throughout this vast space are some of the most ancient objects in our cosmic neighborhood. Globular clusters drift through the halo like cosmic snow globes, each one containing tens of thousands, sometimes hundreds of thousands of stars. These aren't just any stars, they're among the oldest citizens of our galaxy, some reaching back more than 10 billion years. When you peer at a globular cluster through a telescope, the stars pack together so tightly they almost blur into a single ball of light. Gravity holds them in this eternal dance, and they've been waltzing together since before our solar system even existed. It makes you wonder what stories these stellar communities might tell if stars could speak of the eons they've witnessed. The chemistry of halo stars tells fascinating tales about the early universe. Many contain very few heavy elements, just hydrogen and helium mostly. This might sound boring, but it's actually extraordinary. These stars formed when the universe was young and simple, before generations of stellar death and rebirth had scattered heavier elements like carbon and oxygen through space. Every heavy element in your body, from the calcium in your bones to the iron in your blood, was forged inside ancient stars. But halo stars remember a time before this cosmic enrichment happened, when the universe was made of simpler stuff. They're like time capsules, preserving the memory of a more innocent cosmos. Dark matter dominates the halo, though you can't see it directly. This invisible substance outweighs all the visible stars and gas by enormous amounts. The dark matter halo extends far beyond anything we can observe with telescopes, creating a gravitational scaffold that holds our entire galaxy together. Scientists estimate that for every gram of ordinary matter we can see, there are about 5 grams of dark matter we cannot. It's humbling to realize that most of our cosmic neighborhood consists of something we don't understand, something that remains completely mysterious, despite decades of searching. The halo bears scars from our galaxy's violent past. Long streams of stars arc through this region, marking the remains of smaller galaxies that wandered too close to the Milky Way. Gravity slowly tore these dwarf galaxies apart, spreading their stars across vast distances like cosmic spaghetti. One such stream, called the Sagittarius Stream, comes from a dwarf galaxy that's still being shredded as we speak. Over millions of years, this small galaxy has been stretched into a thin line of stars that wraps around our entire galaxy multiple times. It's a cosmic crime scene, frozen in slow motion. These stellar streams help astronomers reconstruct our galaxy's history, revealing how many smaller galaxies we've consumed over billions of years. Our Milky Way has been quite the cosmic cannibal, growing larger by devouring its neighbors. There's something both disturbing and natural about this process, like watching a larger fish swallow smaller ones in an aquarium. Hot gas fills much of the halo space, though it's spread incredibly thin. This gas glows at temperatures of millions of degrees, heated by shock waves from ancient stellar explosions and gravitational interactions. You could fit this entire gas reservoir into a volume the size of Earth's atmosphere, yet it's spread across a region larger than our solar system. This diffuse gas might seem unimportant, but it serves as a reservoir that slowly feeds star formation in the galactic disk. Like a cosmic circulatory system, gas flows inward from the halo, providing raw material for new generations of stars. Without this steady supply, star formation would have ceased long ago. The Magellanic Clouds, those fuzzy patches visible in southern skies, orbit within our galaxy's halo. These small galaxies trail streams of gas behind them as they orbit, like cosmic comets with tails millions of light years long. Eventually, these companions will either be torn apart or merge completely with our galaxy. Observing the halo requires patience and specialized techniques. Its stars are faint and scattered, unlike the dense star fields of the galactic disk. Astronomers often study the halo by looking for its effects on background light, watching how distant quasars dim and brighten as halo material passes in front of them. The halo connects our local galactic neighborhood to the larger cosmic web beyond. It serves as a transition zone between our galaxy's dense interior and the nearly empty spaces between galaxies. In this sense, the halo represents a frontier, the boundary between the familiar and the unknown. Most remarkably, the halo preserves evidence of cosmic evolution spanning nearly the entire age of the universe. Its oldest stars formed when the cosmos was less than a tenth its current age, while ongoing mergers and interactions continue shaping its structure today. This makes the halo both a museum of cosmic history and an active participant in our galaxy's future evolution. Looking up at night, knowing this vast, ancient structure surrounds us, changes how you perceive our place in space. We're not just orbiting within a flat spiral galaxy, we're embedded deep inside a three-dimensional system that extends far beyond anything visible to the naked eye. The halo reminds us that even the most familiar cosmic objects hide depths and complexities that challenge our understanding. When we talk about what exists above or below our solar system, we first need to understand something quite remarkable. Space has no natural up or down. There is no ceiling above us, no floor beneath our feet. This absence of direction might seem obvious, but it reveals something profound about our human need to create order from chaos. Astronomers have solved this puzzle by establishing what they call the ecliptic plane. Think of it as an invisible sheet of paper stretched across the entire solar system. This sheet follows the path that Earth takes as it circles the Sun. From this imaginary surface, we can finally say what lies north, what lies south, what sits above us, and what rests below. The ecliptic plane tells a story that reaches back billions of years. When our solar system was young, everything existed as a massive spinning disk of gas and dust. The Sun had not yet formed. The planets were nothing more than scattered particles, drifting in this cosmic whirlpool. But spin has power, and gravity has patience. Over millions of years, this rotating disk began to flatten. Most of the material settled into the same general level, like cream settling on milk. From this flattened disk, the planets were born. This is why, when we look at our solar system today, nearly every planet orbits in roughly the same flat sheet of space. Mercury tilts a little bit away from this pattern. Pluto tilts quite a lot, but overall, the planets line up within just a few degrees of one another. They remember their birth, locked forever into the geometry of that ancient, spinning disk. Because Earth's orbit defines this plane, something interesting happens in our sky. The Sun appears to follow the same path throughout the year. As Earth makes its yearly journey, the Sun seems to move along a predictable route against the background stars. This path is what we see as the ecliptic, and it explains why the zodiac constellations all lie along the same line in the sky. The Moon follows this path too, so do the planets. On a clear night, when you see several planets strung across the sky like pearls on a thread, you are seeing the trace of this invisible map. You are witnessing the remnant of that primordial disk, still governing the motions of worlds. This invisible framework gives us our orientation for the entire solar system. If you imagine a line sticking straight up from the ecliptic plane, it points toward what astronomers call the North Ecliptic Pole. The opposite direction points toward the South Ecliptic Pole. With these reference points, we can finally talk about above and below in a meaningful way. Above us means toward the north side of the ecliptic. Below us means toward the south. These directions are human constructs, but they reflect real physics. They describe the actual flattening of orbits into a disk, the genuine architecture of our cosmic neighborhood. The ecliptic plane also reveals the distribution of smaller bodies throughout the solar system. The asteroid belt, sitting between Mars and Jupiter, spreads mostly along this same plane. The Kuiper belt, stretching beyond Neptune, aligns with it as well. Even the distant scattered disk of icy objects follows this general orientation. These belts and rings are like faint echoes of the original formation process. They cling to the same flattened shape that gave birth to the planets. Above and below the plane, far fewer objects wander. The vast majority of the solar system's matter remains tied to this invisible sheet, loyal to the pattern established billions of years ago. Astronomers use the ecliptic as a coordinate system for mapping the entire sky. Just as sailors once used latitude and longitude to navigate Earth's oceans, astronomers use ecliptic coordinates to navigate the universe. This invisible grid allows precise measurements linking Earth's motion to the positions of distant stars and galaxies. The inclination of planetary orbits adds interesting variation to this cosmic map. Mercury tilts about 7 degrees relative to the ecliptic. Pluto tilts about 17 degrees. These differences mean that sometimes planets wander slightly above or below the invisible sheet. Over time, their paths cross back and forth like gentle waves on a calm sea. The ecliptic remains the baseline, but the dance of orbits adds complexity. This gentle wavering reflects the intricate pull of gravity, the way massive objects influence one another across vast distances. Looking above the plane, we can find these wanderers rising briefly before dipping back down. Comets bring even more variety to this cosmic choreography. Many of them originate from the Oort cloud, a spherical shell of icy bodies far beyond the planets. When these ancient remnants are nudged inward toward the sun, their orbits can be tilted at any angle. They cut across the ecliptic in dramatic paths, like arrows shot from random directions. These visitors remind us that while the ecliptic defines the dominant structure of our solar system, it does not bind everything. Above and below, far beyond the plane, objects exist, with their own orientations, their own histories. The invisible map is strong and persistent, but it cannot control every wanderer. The ecliptic plane itself is not permanently fixed against the backdrop of our galaxy. It slowly shifts due to gravitational influences, a process astronomers call precession. Over tens of thousands of years, the orientation of the plane changes slightly, altering the position of the ecliptic poles. This long, slow movement reminds us that even the frameworks we create are not eternal. The invisible map of orbits appears steady on human timescales, but on cosmic ones, it drifts. It responds to the subtle pull of other planets and the larger forces of our galaxy. When astronomers look above the plane, toward the north ecliptic pole, they gaze into a region of sky away from our galaxy's center. This gives them a clearer view of distant galaxies, a window into the universe beyond our cosmic neighborhood. When looking below, toward the south ecliptic pole, they see a different slice of the universe entirely. These directions matter for planning observations, for choosing the best times to study the cosmos beyond our solar system. The ecliptic plane serves not just as a local reference, but as a tool that connects our orbit to the wider universe. Spacecraft missions also depend heavily on this invisible map. Journeys to other planets are usually planned along the ecliptic, because that is where the planets travel. Launching outside this plane requires significantly more energy, making missions less efficient and more expensive. The ecliptic is not just an abstract reference for astronomers. It is a practical guide for exploration. Above and below the plane, spacecraft rarely venture unless there is a compelling scientific reason. Most of our exploration remains tied to this flattened sheet, the same sheet that has guided planetary motion since the very beginning. If you could somehow travel far away and look down on our solar system from above the ecliptic, you would see something remarkable. The system would appear as a series of nested circles, each planet tracing its predictable path around the sun. The asteroid belt would form a rough band of debris. The Kuiper belt would create a broader ring of icy objects. Comets and tilted objects would be the obvious exceptions, cutting across at unexpected angles, like rebellious dancers breaking from formation. From this distant perspective, the invisible map would become visible. The logic of the plane would be undeniable. The flattening would strike you as both beautiful and inevitable. Our solar system is not a random scatter of objects drifting through space. It is a disk, organized and structured, with the ecliptic plane at its very core. This organization speaks to something deeper about the nature of the universe. Even in the vast openness of space, patterns emerge. Structures form. Order arises from apparent chaos. The planets are not wandering aimlessly through the void. They are bound to this shared sheet, forever carrying the memory of their violent, beautiful birth. Above and below this plane, exceptions certainly exist. Rogue asteroids follow strange paths. Ancient comets dive in from impossible angles. But the vast majority of objects remain faithful to the map, loyal to the pattern established when the universe was young, and our corner of space was nothing more than swirling dust and dreams of worlds yet to come. The universe has this fascinating way of offering us different perspectives, and one of the most intriguing views comes from looking beneath our galaxy's disk. While many people think about gazing up at the stars, there's something equally profound about looking down, straight through the bottom of the Milky Way. When we peer in this direction, we're essentially looking through what astronomers call the South Galactic Pole. It's like having a clear window that cuts right through all the cosmic clutter. The thick dust and gas that normally blocks our view, all those particles floating around in the galaxy's main disk, they're mostly absent here. This gives us an incredibly clean line of sight into the deeper universe. The constellation sculptor marks this special direction. Now, Sculptor isn't one of those bright, flashy constellations that immediately catches your eye. Its stars are modest, almost humble in their appearance. But don't let that fool you, because this faint patch of sky holds extraordinary importance for understanding our place in the cosmos. What makes this direction so remarkable is how it mirrors the view we get when looking up through the galaxy's north pole. Both directions offer these pristine windows, free from the interference of our galaxy's busy central plane. It's almost like the universe designed these two escape routes, one pointing up, one pointing down, each giving us a complementary perspective on everything beyond our stellar neighborhood. The clarity we get from looking through the South Galactic Pole has made it invaluable for studying the most distant parts of the universe. When scientists want to measure that faint afterglow from the Big Bang, the cosmic microwave background radiation, they often point their instrument toward these galactic poles. The radiation is there everywhere, spread across the entire sky, but it's much easier to detect when you're not looking through all the dust and stars of the Milky Way's disk. This ancient light carries the fingerprints of the universe when it was just a baby, less than 400,000 years old. Back then, the cosmos was finally cooling down enough for the first atoms to form, and light could travel freely for the first time. That light has been streaming through space ever since, carrying information about the universe's early structure. By studying tiny variations in this background glow, scientists can piece together how galaxies and clusters first began to form. But the South Galactic Pole doesn't just give us views of the most distant universe, it also opens up a window to some of our nearest galactic neighbors. About 10 to 12 million light-years away, in this same direction sits a collection of galaxies called the Sculptor Group. Now, 12 million light-years might sound impossibly far, but in cosmic terms, these galaxies are practically next door. One member of this group, often simply called the Sculptor Galaxy, puts on quite a spectacular show. It's what astronomers call a starburst galaxy, meaning it's going through an incredibly active period of star formation. New stars are being born at a rapid pace, lighting up the galaxy with fresh energy. When we look at it through telescopes, we can see it tilted at just the right angle to show off its spiral structure, complete with dark dust lanes where new stars are forming. The fact that we can observe this galactic fireworks display so clearly is partly thanks to our clean line of sight through the South Galactic Pole. Without all that intervening dust from our own galaxy, we get front row seats to watch how other galaxies evolve and grow. Looking in this direction also takes us through our own galaxy's halo, that vast spherical cloud of stars, clusters, and dark matter that surrounds the Milky Way's disk. The halo extends just as far below the galactic plane as it does above, and it's filled with some truly ancient objects. Globular clusters drift through this region, dense swarms of stars that can contain hundreds of thousands of members each. These clusters are incredibly old, many of them over 10 billion years old, making them some of the first structures to form in our galaxy. They're like stellar time capsules, preserving information about what the universe was like when it was much younger. What's particularly fascinating is that many of these ancient star clusters don't follow the organized rotation of the galaxy's disk. Instead, they follow their own independent orbits, swooping in great loops through the halo. Some pass high above the galactic plane, others dive deep below it, and their chaotic paths tell us something important about how our galaxy formed. The halo also contains something even more mysterious: the scattered remains of smaller galaxies that the Milky Way has consumed over billions of years. These stellar streams stretch across the southern sky, like faint ribbons of light, each one representing a galaxy that was torn apart by our galaxy's gravitational pull. By mapping these streams, astronomers can work backward to understand the Milky Way's growth, like archaeologists piecing together ancient history from scattered artifacts. There's something almost poetic about the idea that when we look toward the South Galactic Pole, we're seeing the ghosts of long-dead galaxies, their stars now scattered throughout our galaxy's outer regions. Each faint stream of stars tells a story of cosmic cannibalism, of larger structures growing by absorbing smaller ones. And then there's the dark matter. This invisible substance makes up most of the mass in our galaxy's halo, and it extends just as far below the galactic disk as it does above. We can't see dark matter directly, but its gravitational influence shapes everything around it. The orbits of those globular clusters, the paths of those stellar streams, even the overall structure of our galaxy, all of it is controlled by this unseen cosmic framework. When we gaze toward the South Galactic Pole, we're looking into this invisible architecture that holds everything together. It's humbling to realize that most of what's out there, the very foundation that our galaxy is built on, remains completely hidden from our eyes. The Southern Hemisphere offers unique advantages for exploring this direction. Astronomers in places like Chile, Australia, and South Africa get clearer views of the Sculptor region and its galaxies. Some of the world's most powerful telescopes sit on mountaintops in the Andes, taking advantage of the clear, dry air and the southern sky's window into nearby galaxy groups. These observatories have revealed incredible details about our cosmic neighborhood. They've shown us star formation happening in real time in the Sculptor galaxy, mapped the distribution of dark matter in nearby clusters, and traced the cosmic web that connects galaxies across vast distances. There's something profound about how the universe provides us with these two clear windows, north and south, above and below our galaxy's cluttered disk. It's almost as if the cosmos is designed to give us perspective, to let us step outside our immediate stellar neighborhood and see the bigger picture. The South Galactic Pole reminds us that direction matters, even in the seemingly directionless void of space. By defining up and down relative to our galaxy's structure, we create a framework for understanding our place in the larger universe. Below the disk lies not emptiness, but a rich tapestry of ancient stars, nearby galaxies, invisible matter, and the faint echo of the universe's birth. Each time we point our instruments in this direction, we're essentially climbing out of our galaxy's basement and getting a clearer view of the cosmic neighborhood beyond. It's a reminder that sometimes, to truly understand where we are, we need to look at where we're not, to peer through the windows that take us outside our immediate cosmic home and into the vast structures that surround us. The invisible boundaries of our solar neighborhood stretch far beyond anything we might expect. Picture a vast, spherical shell of frozen objects, so distant that light takes over a year just to cross from one side to the other. This is the Oort cloud, a cosmic snow globe that wraps around everything we call home. When a Dutch astronomer named Oort looked up at the night sky in 1950, he noticed something peculiar about certain comets. These weren't your typical visitors with predictable paths. These comets had orbits that lasted thousands, sometimes millions of years. They seemed to arrive from nowhere, following paths so elongated and random that they couldn't possibly come from the known regions of space. The mystery deepened when Oort realized these wandering iceballs had to originate somewhere. Their trajectories pointed back to a source so far away that it existed more as a mathematical concept than a visible reality. This led to one of astronomy's most elegant theories, a solution hiding in plain sight, or rather, in plain darkness. Imagine standing in your backyard and realizing that your property extends not just to the fence you can see, but to a boundary so far away that you'd need a spaceship traveling for centuries just to reach it. The Oort cloud begins roughly 2,000 times farther from the Sun than Earth is. To put that in perspective, if Earth's distance from the Sun was the length of a football field, the inner edge of the Oort cloud would start somewhere in the next state over. But that's just the beginning. The outer reaches of this cosmic shell extend nearly halfway to the closest star to our Sun. We're talking about a structure so enormous that if you could somehow see it from the side, it would look like a giant soap bubble with our entire solar system, including all the planets, sitting as a tiny speck at the center. Every few years, we get visitors from this distant realm, those spectacular comets that light up our skies, trailing brilliant tails across the darkness, are actually messengers from the Oort cloud. They've been nudged from their distant homes by the gentle tug of a passing star, or by the subtle gravitational massage of our entire galaxy, slowly rotating through space. Think about what this means for a moment. These comets are time capsules, frozen libraries that have been sitting in the cosmic deep freeze for billions of years. When they finally make their journey inward, heated by our sun until they develop those magnificent tails. They're releasing materials that date back to when the solar system was young and chaotic. The story of how the Oort cloud formed reads like a tale of cosmic exile. When the planets were still growing, sweeping up debris and settling into their current orbits, countless smaller objects got caught in a gravitational tug of war. Some were flung completely out of the solar system, banished forever to wander between the stars. Others weren't quite given enough energy to escape entirely, so they ended up in these incredibly distant orbits, still technically part of our solar system, but barely feeling the sun's influence. Over millions and millions of years, these exiled objects arranged themselves into a spherical shell around everything we know. Unlike the flat disk where the planets orbit, the Oort cloud extends in all directions, up, down, and sideways, forming a three-dimensional boundary that defines the true edge of our solar system's gravitational influence. What makes this structure even more fascinating is how delicate its existence really is. Out at those incredible distances, the sun's gravity is so weak that other forces start to matter. When another star passes relatively nearby, which happens every few million years or so, it can shake the Oort cloud like a tree, sending showers of comets toward the inner solar system. Even our galaxy itself plays a role. The Milky Way creates what astronomers call tidal forces, a gentle but persistent stretching effect that constantly stirs the Oort cloud. It's similar to how the moon creates tides on Earth's oceans, but operating on a scale that's almost impossible to comprehend, involving distances measured in light years and time scales measured in millions of years. Scientists estimate there might be trillions of objects floating in this distant shell. Most are probably no bigger than mountains, chunks of ice and rock that formed during the solar system's violent youth, but some could be much larger, perhaps even the size of small moons, drifting silently in orbits so wide that they take millions of years to complete a single trip around the sun. The space between these objects is so vast that if you were somehow transported to the Oort cloud, you'd likely see nothing but stars in every direction. The nearest Oort cloud object might be farther away than Mars is from Earth. It's a population that's simultaneously enormous in number, but incredibly sparse in density. This raises profound questions about where our solar system actually ends. If we only count the planets, we might say it ends at Neptune. Include the asteroid belt and some smaller objects, and we could push that boundary a bit farther. But if we include the Oort cloud, then our solar system suddenly becomes something that extends nearly halfway to the next star. In a sense, we exist within a cosmic onion, with layer after layer of structure, extending outward from the sun. The planets occupy the innermost layer. Then comes the Kuiper belt where Pluto lives, then the scattered disk of other icy objects, and finally the Oort cloud as the outermost shell. Each layer tells part of the story of how gravity and time have organized matter in our little corner of the universe. Recent discoveries have made the Oort cloud even more intriguing. We've now detected objects passing through our solar system that clearly come from other stars. These interstellar visitors might be similar to our own Oort cloud objects, knocked loose from distant stellar systems and now wandering through space. This suggests that there might be a slow exchange of material between star systems, with each stellar neighborhood occasionally sharing pieces of its ancient past with its neighbors. The chemical composition of Oort cloud objects holds clues about conditions in the early solar system. When these comets approach the sun and start to evaporate, the gases they release carry signatures of molecules that formed billions of years ago. Some of these molecules are the building blocks of life itself, suggesting that the Oort cloud might be a vast repository of the materials that made life on Earth possible. This connects us to an even grander story. Earth's water might have come partially from Oort cloud comets that crashed into our planet during its youth. The organic compounds necessary for life might have arrived the same way. In essence, we might all be made partly of materials that spent billions of years in the cosmic deep freeze, waiting for the right gravitational nudge to begin a million-year journey toward the inner solar system. The invisibility of the Oort cloud doesn't make it less real, it makes it more mysterious. We know it's there because of the mathematical precision of comet orbits, because of the chemical signatures in their tails, because of the predictable patterns in which they arrive. It's a perfect example of how science can reveal hidden structures Through careful observation and logical deduction, looking up at the night sky, it's humbling to realize that everything we can see, all the planets and moons and asteroids, represents just the tiniest fraction of the space that actually belongs to our solar system. The real boundary lies in darkness so complete and distances so vast that light itself becomes a slow traveler, taking years to bridge the gap between the inner solar system and its outermost frontier. Far beyond where planets circle, ancient frozen remnants drift in endless darkness. The Oort cloud holds trillions of these icy time capsules, each one a preserved fragment from the solar system's birth. Most people picture this region as empty space, but it's actually teeming with potential visitors, waiting for the right gravitational nudge to begin their long journey sunward. These distant wanderers spend almost their entire existence in complete solitude. At such enormous distances, sunlight barely reaches them, making them invisible even to our most powerful telescopes. They exist in a kind of suspended animation, unchanged for billions of years. While planets evolved and transformed, developing complex surfaces and atmospheres, these small bodies remained exactly as they were when the solar system first formed. The composition of a comet tells a remarkable story. They're basically dirty snowballs, mixtures of ice, rock and dust, that never grew large enough to become planets. This primitive makeup makes them incredibly valuable to scientists. Each comet carries within it the original recipe of our cosmic neighborhood, the same materials that swirled around the young sun in a vast isthmus of gas and debris. What's fascinating is how these objects eventually begin their journey inward. The triggers can be surprisingly subtle. A star passing several light years away might disturb their orbits just enough to start the process. The slow tidal forces from our galaxy can shift their paths over millions of years. Even tiny gravitational tugs from distant planets can accumulate over time, eventually sending a comet tumbling toward the inner solar system. This process happens constantly, but on timescales that dwarf human experience. What appears to us as a sudden appearance is acting breed west. Periods. The universe operates with a patience that makes our longest projects seem like brief moments. When a comet finally approaches the sun, the transformation is dramatic. The frozen surface begins to vaporize, releasing gas and dust that forms a glowing envelope around the nucleus. Solar wind and radiation pressure stretch this material into magnificent tails that can extend millions of miles. These tails always point away from the sun, creating the classic curved appearance we recognize. The beauty of a comet's display masks its underlying fragility. Each close approach to the sun strips away more material, gradually wearing down the nucleus. Some comets shatter completely after repeated visits, breaking into fragments that create meteor showers when Earth passes through their debris. Others simply fade away, their volatile materials exhausted, leaving behind only dark, rocky remnants. This raises an interesting philosophical question about permanence and change. These objects survived unchanged for billions of years in the outer darkness, only to be transformed or destroyed when they finally encounter warmth and light. There's something poignant about this cosmic irony, how the very force that makes them visible also ensures their eventual demise. Comets from the Oort cloud behave differently from their cousins in the Kuiper belt. Kuiper belt comets have relatively short orbital periods, returning every few decades or centuries. But Oort cloud comets take thousands or millions of years to complete their orbits. Some may never return at all, their paths carrying them back into the darkness for longer than human civilization has existed. The spherical shape of the Oort cloud means these long-period comets can approach from any direction. Unlike planets and asteroids that mostly orbit in the same plane, comets arrive from above, below, and every angle in between. This reminds us that our solar system isn't just a flat disk, but is surrounded by this enormous spherical shell of dormant travelers. Early in Earth's history, these cosmic visitors may have played a crucial role in making our planet habitable. Many scientists believe comets delivered much of Earth's water, crash landing in spectacular impacts that helped fill our oceans. The isotopic signature of water in some comets closely matches that found in Earth's seas. suggesting a deep connection between our world and these distant wanderers. Comets may have also delivered organic molecules, the complex carbon-based compounds that form the building blocks of life. If this theory is correct, then the long wait in the outer darkness wasn't meaningless. These objects were essentially cosmic seed banks, storing the ingredients for life until chance encounters sent them earthward at just the right time. The scale of the Oort cloud population is staggering. Current estimates suggest there could be trillions of individual objects waiting out there, far more than all the asteroids, planets, and moons combined. Most will never be disturbed, continuing their silent orbits until the sun itself burns out. But even if only a tiny fraction ever venture inward, that's enough to supply our solar system with comets for billions of years to come. Some comets meet dramatic fates when they finally approach the sun. Sun-grazer comets dive so close they actually scrape the solar atmosphere, vaporizing completely in temperatures exceeding 1,000,000 degrees. Others make their closest approach and then swing back outward on trajectories that won't bring them back for millennia. The orbital mechanics involved reveal just how vast these elliptical paths truly are. Space missions have given us intimate portraits of these ancient objects. Robotic explorers have landed on comets, analyzed their composition, and even collected samples from their glowing tails. These close-up studies reveal surfaces that are surprisingly complex, with jets of gas erupting from specific locations, creating their own weather systems on a miniature scale. The exchange of comets between star systems adds another layer of complexity. Gravitational encounters can eject objects entirely, sending them on one-way trips to interstellar space. Our solar system may have also captured comets from other stars, immigrants from distant neighborhoods that now wait alongside our original population. This cosmic trade blurs the boundaries between stellar systems, connecting us to the broader galactic community. There's something humbling about contemplating these patient travelers. They represent a kind of cosmic endurance that puts human timescales in perspective. While civilizations rise and fall, species evolve and go extinct, and continents drift across planetary surfaces, these small worlds continue their ancient dance, largely unchanged since the solar system's youth. The darkness that conceals them isn't empty or lifeless, but pregnant with potential. Each frozen nucleus carries the possibility of becoming a spectacular celestial display, lighting up future skies for observers who may be very different from ourselves. Their waiting isn't passive, but represents a kind of cosmic readiness, a connection between our solar system's past and its distant future. When we look up at a comet's glowing tail stretched across the night sky, we're witnessing the final act of an incredibly long story. That beautiful apparition is temporary, but behind it lies the vast reservoir of the Oort cloud, where countless others continue their patient vigil, drifting through the deep darkness, waiting for their turn to journey toward the light. The space around us holds travelers that don't belong to our solar system at all. These interstellar wanderers formed around distant stars, only to be kicked out, drifting through the galaxy for millions of years before passing near us. They arrive from unexpected directions, cutting across our solar system at steep angles, some emerging from beneath the plane of planets, moving upward through our cosmic neighborhood. In 2017, astronomers confirmed the first such visitor. They named it Oumuamua, a Hawaiian word meaning scout or messenger, arriving first. This object moved too fast for our sun's gravity to hold it, its trajectory clearly showing it came from interstellar space. It swung past the sun and headed back out, giving us only a brief window to study it before it was already receding into the darkness. Oumuamua puzzled scientists with its strange properties. Its unusual shape, odd motion, and lack of a visible tail left researchers scratching their heads. Some thought it might be an unusual comet or asteroid. Others proposed more exotic explanations. Whatever it was, it clearly wasn't born here, just passing through like a stranger on an endless journey. 2 years later, another interstellar object appeared, named Borisov after the amateur astronomer who spotted it. This one behaved more like a typical comet, sporting a coma and tail as it released gas and dust approaching the sun. But its speed and orbit revealed it too came from beyond our system. Borisov gave scientists their first clear look at the chemistry of a comet from another star, showing many of the same compounds found in our own solar system comets. These discoveries confirmed what astronomers had long suspected. Our solar system's Oort cloud, filled with trillions of comets, regularly ejects objects into interstellar space. Other stars likely have similar clouds of icy remnants, and they eject objects too. The galaxy must be filled with countless wanderers, drifting between stars, occasionally passing through other systems like ours. The fact that we've only recently discovered these objects reflects our improving technology. Modern telescopes can scan wide regions quickly, detecting faint moving objects that would have been missed decades ago. Future surveys will likely reveal many more, some arriving from beneath our solar system's plane, unnoticed until they're already close. Each interstellar visitor carries material from environments we can't otherwise reach. Our spacecraft are limited to our own system, and even Oort cloud comets are part of our solar system's history. But these visitors bring samples from other systems, pieces of distant worlds that formed under different conditions. Borisov's chemistry suggested that comet formation is similar throughout the galaxy, while Oumuamua's unusual properties hinted at greater diversity than we imagined. The arrival of these objects blurs the boundary between our own distant comets and those drifting through the galaxy. Some bodies in our Oort cloud may eventually be ejected, becoming visitors elsewhere. Some objects passing through our system may once have belonged to other stars' comet clouds. The galaxy isn't divided into isolated systems, but threaded with constant exchanges, a sharing of material across vast distances. Earth might even capture such an object someday. If conditions are right, an interstellar body could lose enough speed to become bound to our system. Over billions of years, this may have happened many times. Some comets we consider part of our Oort cloud may actually be immigrants from other stars, fragments of alien systems, indistinguishable from our own, except in origin. The motions of these visitors remind us of the galaxy's immense scale. Even moving at tens of kilometers per second, it takes hundreds of thousands of years for objects to cross from one region to another. When we glimpse one passing through, we're seeing just a moment in a voyage that began millions of years ago and will continue long after it leaves us. Some scientists speculate these visitors might carry organic molecules, the building blocks of life. If comets delivered such molecules to planets as they may have to Earth, then interstellar comets could carry them between systems over billions of years. This could provide a mechanism for seeding life across the galaxy, though whether this has ever happened remains unknown. Between these occasional visitors and the structured regions of space lies something quieter, vast lanes where there's almost nothing at all, not the bustling flow of cosmic rays, not bright star-forming clouds, but emptiness, thin and silent. Beneath our solar system's plane, through the depths beyond the comets, lie these quiet lanes. The idea of emptiness in space can be difficult to picture. Even the interstellar medium, which we call empty, still has atoms spread across each cubic centimeter. But the quiet lanes are regions where matter is far less concentrated, densities so low that random collisions are negligible. These are deserts in space, wide stretches separating oases of matter. The galaxy isn't uniformly filled with stars and gas. It's patchy, structured with dense clouds here and wide gaps there. Our solar system drifts through these regions. As it orbits the galaxy, sometimes passing through clouds, sometimes through quieter spaces. Right now we're thought to be within a local interstellar cloud, but beyond it lies a broader local bubble, a cavity of low-density gas. The silence of these lanes isn't absolute. Cosmic rays still pass through, high-energy particles crossing light years without pause. Magnetic fields thread through, weak but present. A few atoms of hydrogen and helium still drift, sparse but not absent. Yet compared to dense star-forming clouds, these lanes are barren, the resting spaces of the galaxy, calm between bursts of activity. One way to imagine them is as an ocean where currents sometimes converge and storms churn, but other areas remain calm, flat, undisturbed. The quiet lanes are like those calm stretches, not featureless, but still, where the galaxy's activity slows and little disrupts the silence. For spacecraft moving outward, beyond our sun's influence, these are the spaces they must cross. Some directions lead through clouds and turbulence, others through quiet lanes. Others through quiet lanes. The emptiness has practical importance for astronomy too. When looking through these lanes, we can see farther into the universe, since dust and gas scatter and absorb light less here. It's also in these quiet lanes that interstellar visitors may drift unnoticed. Objects could travel for millions of years through such regions without interacting with anything, making these lanes ideal pathways for wanderers, the highways of the galaxy, open and empty. The scale of these empty regions is enormous. A cubic meter of air on Earth contains about 25 quintillion molecules, while a cubic meter of interstellar space may contain just a handful of atoms. The difference is so extreme, it's hard to picture, yet this is the reality of quiet lanes, space so empty, it's almost nothing, stretching distances that dwarf our solar system. Even in this emptiness, subtle structures exist. Magnetic fields ripple through, shock waves from ancient supernovae echo, faintly, particles occasionally collide, generating faint radiation. The quiet lanes aren't truly empty, but are low points in the galaxy's rhythm, places where activity fades, but never fully disappears, but never moves through. These quiet lanes matter because they influence our solar system's environment. As our sun moves through the galaxy, its protective heliosphere expands or contracts depending on surrounding density. In quiet lanes with little external pressure, the heliosphere expands farther, giving us a larger shield. In denser clouds, it shrinks, exposing Earth to more cosmic rays. The idea of emptiness might feel unsettling, but it brings perspective. The galaxy isn't crowded everywhere. It's mostly made of space like this, quiet, sparse, thin. The bright stars and nebulae we see in photographs are exceptions, not the rule. Most of the Milky Way consists of these quieter stretches, vast deserts between oases. In these stretches, time feels different. With so little to mark events, no collisions, no star formation, no bright bursts, the lanes are places of waiting. Comets may pass through, interstellar objects may drift, but overall stillness remains. For billions of years such regions have existed, and for billions more they'll continue, empty yet essential, connecting the galaxy's active parts with silence. Imagine looking up at the night sky and seeing what appears to be a perfectly flat band of light stretching across the darkness. That's our Milky Way galaxy as we see it from Earth. But this view, as beautiful as it is, tells us only part of the story. If we could somehow step outside our galaxy, travel far enough to see it from a distance, we'd discover something quite remarkable. The Milky Way isn't flat at all. Picture a vast ocean, frozen in the middle of a gentle wave. One side rises up, the other dips down, creating this graceful, curved shape. That's exactly what our galaxy looks like. Astronomers call this the galactic warp, and it's one of those features that completely changes how we think about our cosmic home. Radio telescopes first revealed this secret back when scientists were mapping hydrogen gas throughout the galaxy. They expected to find everything lying nice and neat, in the same plane. Instead, they discovered that the outer parts of the galaxy were tilted, rising on one side, falling on the other. Later observations of actual stars confirmed this bending, though stars don't warp quite as dramatically as the gas does. The whole structure curves into what you might call a shallow S shape. Above us, one part of the galactic disk lifts higher into space. Below us, another part dips lower. And we're riding along this bent surface as our solar system orbits the galaxy's center. Sometimes we're slightly above the average plane, sometimes slightly below, depending on exactly where the warp carries us. What causes this cosmic bending? Well, galaxies aren't isolated islands floating alone in space. They have neighbors, and those neighbors tug on them. The large and small Magellanic Clouds, two smaller galaxies that orbit the Milky Way, probably play a role. Their gravity creates ripples in our galaxy's structure, like dropping stones into a pond. Dark matter adds another layer to this story. The invisible halo of dark matter surrounding our galaxy might not be perfectly round. If it's lopsided in any way, its uneven gravitational pull could twist the visible disk into this warped shape. Past collisions with other galaxies, streams of stars flowing through space, even the motion of gas in the outer regions, all these forces work together to bend and flex the galaxy. Here's something fascinating though. Our Milky Way isn't unique in being warped. When astronomers look at other spiral galaxies edge on, they see the same kind of bending. Galaxies like NGC 4013 show these beautiful curved shapes, their outer regions gracefully arcing above and below the central plane. It seems that warps are actually quite common, perhaps inevitable when galaxies interact with their surroundings. From where we sit inside the galaxy, this warping is nearly invisible to us. The stars around us are close enough that we can't easily detect the overall bending with our eyes. It's only when scientists map thousands and thousands of stars that the pattern emerges, like stepping back from a pointillist painting to see the bigger picture. The scale of this warp is truly staggering. Our galaxy stretches about 100,000 light-years across, and the warping raises and lowers the outer edges by several thousand light-years. Imagine an ocean frozen mid-wave, but with crests and troughs spanning distances that light itself takes millennia to cross. That's the scale we're talking about. This bending isn't just a static shape either. It affects how stars and gas move throughout the galaxy. The warping creates regions where material flows in slightly different directions, where gravity pulls at angles that aren't quite aligned with the central plane. This influences where new stars form, creating subtle asymmetries in the galaxy's structure. It shapes how gas settles and flows, affecting even the grand spiral arms we see in photographs. Some researchers think the warp might actually be moving, like a wave slowly rippling through the galaxy over millions of years. If that's true, then what we see today is just one moment in a cosmic dance that's been going on for billions of years. The bend we observe might rise and fall like a tide in this stellar ocean. Our solar system itself sits at an angle to the galaxy's main plane. Earth's orbit defines what astronomers call the ecliptic plane, and this is tilted about 60 degrees relative to the galaxy's disk, so even our local sense of up and down doesn't perfectly align with the galaxy's structure. Add the warp to this picture, and the geometry becomes wonderfully complex. When we think about direction in space, we're always choosing a frame of reference. Above and below in our solar system terms don't match exactly with above and below in galactic terms. It's like having multiple maps of the same territory, each useful for different purposes. The galaxy holds many secrets beyond its warped shape. Scattered throughout its halo are streams of stars, long faint ribbons that mark where smaller galaxies were torn apart long ago. The Sagittarius stream is one of the most prominent, the remnant of a dwarf galaxy that's currently being absorbed by the Milky Way. These streams wrap around our galaxy in great loops, visible only when astronomers analyze the positions and motions of thousands of stars. Each stream tells a story of cosmic cannibalism, preserving the orbital motion of stars long after their original home was destroyed. They're like fossils in space, records of events that happened billions of years ago. The GD1 stream probably came from a disrupted star cluster. The Orphan stream has lost any clear connection to its parent, but its stars still trace their ancient path through space. Between the stars, the galaxy is also threaded with filaments of matter, narrow structures that are even harder to see than the stellar streams. Some are magnetic in nature, visible only in radio wavelengths, as long thin strands of emission. Others are streams of cold gas flowing inward, feeding the galaxy with fresh material for making new stars. High above the galactic disk float clouds of gas, diffuse concentrations moving at speeds that don't match the galaxy's rotation. These high-velocity clouds have various origins, Some are gas stripped from small galaxies passing nearby. Others might be material falling into the Milky Way from intergalactic space. Still others could be fountains of gas thrown upward from the disk by stellar explosions, cooling as they travel and eventually raining back down. The Magellanic Stream is perhaps the most dramatic example of these structures. It's a long ribbon of gas stretching across the southern sky, trailing behind the large and small Magellanic Clouds as they orbit our galaxy. This stream was pulled out by tidal forces, leaving behind a filament of hydrogen that spans more than half the sky. Though invisible to our eyes, radio telescopes map it clearly. These hidden structures, the streams and filaments and clouds, tell us that galaxies are not static objects. They're constantly changing, absorbing smaller systems, exchanging material with their surroundings. The Milky Way is not a finished product, but a living system, shaped by its past and still evolving toward its future. What we see in our galaxy reflects patterns that exist throughout the universe. The cosmic web itself is made of filaments on the grandest scale, with galaxies as the nodes where they intersect. The streams and filaments we find in the Milky Way are smaller echoes of that universal pattern. We're connected to everything else, part of a web that links the smallest star clusters to the largest superclusters of galaxies. When we use words like above and below to describe these cosmic structures, we're applying concepts that come from our daily experience on Earth. Here, gravity defines direction in a way that feels absolute. Drop something, and it falls down. Raise your hand, and it goes up. These directions feel permanent, unchanging. But in space, above and below are relative. Astronomers define the North Galactic Pole as the direction perpendicular to the galaxy's disk on one side, with the South Galactic Pole pointing the opposite way. This gives us a framework for describing positions, but it's a choice of convenience, not an absolute truth. From our perspective within the solar system, we use the ecliptic plane, defined by Earth's orbit, as another reference frame. But this doesn't align perfectly with the galactic plane. Depending on which frame we choose, above and below can mean different things. It's like having multiple maps of the same region, each oriented differently. This relativity of direction extends even further when we consider that the galaxy itself is moving. It's approaching the Andromeda Galaxy, flowing as part of the local group of galaxies, which in turn moves within larger structures. At each scale, up and down get redefined. What's above at one level might not be above at another. Astronauts experience something like this when they orbit Earth. In microgravity, there's no natural up or down inside their spacecraft. One person's ceiling can be another's floor, depending on orientation. Extend this to interplanetary space, and the relativity grows stronger. In interstellar space, only chosen frames of reference remain. Despite this relativity, these concepts remain useful because they help us orient ourselves in the vastness. They provide a way to imagine where things are, to describe positions consistently. Above and below become directions on a map, rather than universal truths. They're tools we adapt to whatever scale we're considering. This perspective can be freeing. It reminds us that the universe isn't bound to our local sense of orientation. There's no absolute center, no absolute up or down, only relationships between objects and the frames we use to describe them. Even the cosmic web has no preferred direction until we choose to map it in a particular way. And yet, these words remain comforting because they give us a way to navigate the infinite. When we ask what lies above or below our solar system, we're really asking how we fit into the larger structure. The answer is that we're always between scales, between the known and unknown, between the solid ground beneath our feet and the endless sky above. Earth feels solid and still, yet it's carried along in all these vast motions. We orbit the sun carries us around the galaxy moves through space. At every level, there's motion, yet from our surface, we feel at rest. This contrast between stillness and motion is part of the perspective we carry as cosmic beings living on a small world. When we return our thoughts to Earth after considering these vast scales, we don't retreat from the cosmos, that acknowledge our place within it. To know that above us lies the galactic halo, streams of stars, and the weight of dark matter is to feel surrounded by mystery. To know that the galaxy itself is warped, like a frozen wave, is to sense the dynamic nature of everything around us. Home isn't small. When we place it in this context, Earth becomes central, not because it's at the center of the universe, but because it's the center of our perspective. From here we observe, measure, and wonder. Our planet is our anchor point for understanding everything else. The cosmic rays flowing through the galaxy, the comets waiting in distant orbits, the empty lanes of space between the stars, all of these remind us how unusual Earth is. Our world is not separate from these cosmic forces, but shaped by them, dependent on them, part of them. Yet it's also where we create meaning, where we ask questions about what lies beyond. To hold this perspective is to weave the far and near together, recognizing that dark matter bends starlight, while gravity shapes our steps, that galaxies collide while clouds drift across our local sunset. We exist in the balance between these scales, at the point where above and below meet in our questioning gaze.